Certified Tester, Advanced Level, Test Analyst, CTAL. Syllabus, v3.1.2, International Software Testing Qualifications Board. Certified Tester Advanced Level, Test Analyst, CTAL-TA. Copyright Notice O. International Software Testing Qualifications Board, ISTQB, is a registered trademark of the International Software Testing Qualifications Board. Copyright O. 2021-2022, the authors of the update v3.1.0, Errata 3.1.1, and Errata 3.1.2. Wim de Cotere, István Forgács, Matthias Hamburg, Adam Roman, Jan Sabak, Marc-Florian Wendland. Copyright O. 2019, the authors of the update 2019, Graham Bath, Judy McKay, Jan Sabak, Eric van Veenendaal. Copyright O. 2012, the authors, Judy McKay, Mike Smith, Eric van Veenendaal. All rights reserved. The authors hereby transfer the copyright to the ISTQB. The authors, as current copyright holders, and ISTQB, as the future copyright holder, have agreed to the following conditions of use. Extracts for non-commercial use from this document may be copied if the source is acknowledged. Any accredited training provider may use this syllabus as the basis for a training course if the authors and the ISTQB are acknowledged as the source and copyright owners of the syllabus, and provided that any advertisement of such a training course may mention the syllabus only after official accreditation of the training materials has been received from an ISTQB recognized member board. Any individual or group of individuals may use this syllabus as the basis for articles and books if the authors and the ISTQB are acknowledged as the source and copyright owners of the syllabus. Any other use of this syllabus is prohibited without first obtaining the approval in writing of the ISTQB. Any ISTQB recognized member board may translate this syllabus provided they reproduce the above-mentioned copyright notice in the translated version of the syllabus. Certified Tester Advanced Level, Test Analyst, CTAL-TA. Revision History. Version, Date, Remarks. 2012 v2.0, 2012 10-19. First version as a separate AL-TA syllabus. 2019 v3.0, 2019 10-19. Major update with overall revision and scope reduction. v3.1.0, 2021-03-03. Minor update with Section 3.2.3 rewritten and various wording improvements. v3.1.1, 2021-05-15. Errata. The copyright notice has been adapted to the current ISTQB standards. v3.1.2, 2022-01-31. Errata. Minor formatting, grammar, and wording defects fixed. For more details, see the release notes. Certified Tester Advanced Level, Test Analyst, CTAL-TA. Table of Contents. Revision History. Table of Contents. Acknowledgements. 0. Introduction to this syllabus. 0.1. Purpose of this syllabus. 0.2. The Certified Tester Advanced Level in Software Testing. 0.3. Examinable Learning Objectives and Cognitive Levels of Knowledge. 0.4. The Advanced Level Test Analyst Exam. 0.5. Entry Requirements for the exam. 0.6. Expectations of Experience. 0.8. Accreditation of courses. 0.9. Level of syllabus detail. 0.10. How the syllabus is organized. 1. The test analyst's tasks in the test process, 150 minutes. 1.1. Introduction. 1.2. Testing in the software development lifecycle. 1.3. Test analysis. 1.4. Test design. 1.4.1. Low-level and high-level test cases. 1.4.2. Design of test cases. 1.5. Test implementation. 1.6. Test execution. 2. The test analyst's tasks in risk-based testing, 60 minutes. 2.1. Introduction. 2.2. Risk identification. 2.3. Risk assessment. 2.4. Risk mitigation. 22. 2.4.1. Prioritizing the tests. 23. 2.4.2. Adjusting testing for future test cycles. 23. 3. Test techniques, 630 minutes. 24. 3.1. Introduction. 25. 3.2. Black box test techniques. 25. 3.2.1. Equivalence partitioning. 25. 3.2.2. Boundary value analysis. 27. 3.2.3. Decision table testing. 28. 3.2.4. State transition testing. 29. 3.2.5. Classification tree technique. 31. 3.2.6. Pairwise testing. 32. 3.2.7. Use case testing. 33. 3.2.8. Combining techniques. 34. 3.3. Experience-based test techniques. 35. 3.3.1. Error guessing. 35. 3.3.2. Checklist-based testing. 36. 3.3.3. Exploratory testing. 37. 3.3.4. Defect-based test techniques. 38. 3.4. Applying the most appropriate technique. 39. 4. Testing software quality characteristics, 180 minutes. 40. 4.1. Introduction. 41. 4.2. Quality characteristics for business domain testing. 42. Certified Tester, Advanced Level, Test Analyst, CTAL. 4.2.2. Functional Appropriateness Testing. 4.2.3. Functional Completeness Testing. 4.2.4. Interoperability Testing. 4.2.5. Usability Evaluation. 4.2.6. Portability Testing. 5. Reviews, 120 mins. 5.1. Introduction. 5.2. Using checklists in reviews. 5.2.1. Requirements reviews. 5.2.2. User story reviews. 5.2.3. Tailoring checklists. 6. Test tools and automation, 90 mins. 6.1. Introduction. 6.2. Keyword-driven testing. 6.3. Types of test tools. 6.3.1. Test design tools. 6.3.2. Test data preparation tools. 6.3.3. Automated test execution tools. 7. References. 7.1. Standards. 7.2. ISTQB and IREB documents. 7.3. Books and articles. 7.4. Other references. 8. Appendix A. 9. Index. Certified Tester Advanced Level, Test Analyst, CTAL. Acknowledgements. This document was produced by the Test Analyst Task Force of the International Software Testing Qualifications Board Advanced Level Working Group. Mette Brun Pedersen, Working Group Chair. Matthias Hamburg, Product Owner. Wim de Couter, István Forgács, Adam Roman, Jan Sabak, Marc-Florian Wendland, Authors. The task force thanks Paul Weymouth and Richard Green for their technical editing, Gary Mogurodi for the glossary conformance checks, and the member boards for their review comments related to the published 2019 version of the syllabus and the proposed changes. The following persons participated in the reviewing and commenting on this syllabus: Gary Agnetz, Armin Born, Chenifan, Claudia Dusa-Zieger, Chen Gang, Kevin, István Gerchak, Richard Green, Ole Krah Hansen, Zolt Hargitai, Andreas Hetz, Tobias Horn, Joan Killeen, Attila Kovacs, Rick Marcellus, Martin Matthias, Blair Moe, Gary Mogurodi, Ingvar Nordstrom, Tal Per, Palma Poliak, Nishan Portoyan, Mele Posthuma, Stuart Reed, Maureen Song, Peter Soter, Luchan Stopp, Benjamin Timmermans, Chris Von Baal, Stephanie Von Dyke, Paul Weymouth. This document was released by ISTQB on 23 Feb 2021. Subsequently, formal, grammar, and wording improvements have been suggested by Tal Per, Stuart Reed, Marc-Florian Wendland, and Matthias Hamburg, which have been implemented and published in the Errata 3.11 and 3.12. The version 2019 of this document was produced by a core team from the International Software Testing Qualifications Board Advanced Level Working Group: Graham Bath, Judy McKay, Mike Smith. The following persons participated in the reviewing, commenting, and balloting of the 2019 version of this syllabus: Laura Albert, Marcus Beck, Henriette Brown-Bocor, Francisca Cano Ortiz, Go Chao Leon, Wim de Couter, Milena Donato, Claudia Dusa-Zieger, Melinda Eckrick Brager, Peter Foldhotson Jr., David Fry, Chen Geng, Matthias Hamburg, Zolt Hargitai, Jai Hongbao, Tobias Horn, Agata Horvath, Beata Karpenska, Attila Kovacs, Josef Kreis, Dietrich Leimsner, Ren Leon, Claire Lohr, Ramit Manohar Kal, Rick Marcellus, Martin Matthias, Don Mills, Blair Moe, Gary Mogurodi, Ingvar Nordstrom, Tal Per, Palma Poliak, Mele Posthuma, Lloyd Prostama, Lloyd Roden, Adam Roman, Abhishek Sharma, Peter Soter, Luchan Stopp, Andrea Sabot, Jan Takak, Benjamin Timmermans, Chris Von Baal, Eric von Veenendaal, John Versmissen, Karsten Weiss, Robert Workhoven, Paul Weymouth. The version 2012 of this document was produced by a core team from the International Software Testing Qualifications Board Advanced Test Analyst: Judy McKay, Chair, Mike Smith, Eric von Veenendaal. At the time the Advanced Level syllabus was completed, the Advanced Level Working Group had the following membership: alphabetical order: Graham Bath, Rex Black, Maria Clara Schokayer, Deborah Friedenberg, Bernard Holmes, Vice Chair, Paul Jorgensen, Judy McKay, Jamie Mitchell, Thomas Mueller, Klaus Olsen, Kenji Onishi, Mele Posthuma, Eric Redu-Kosker, Jan Sabak, Hans Schaefer, Mike Smith, Chair, Jeff Thompson, Eric von Veenendaal, Tsuyoshi Yumoto. The following persons participated in the reviewing, commenting, and balloting of the 2012 version of the syllabus: Laura Albert, Marcus Beck, Henriette Brown-Bocor, Francisca Cano Ortiz, Go Chao Leon, Wim de Couter, Milena Donato, Claudia Dusa-Zieger, Melinda Eckrick Brager, Peter Foldhotson Jr., David Fry, Chen Geng, Matthias Hamburg, Zolt Hargitai, Jai Hongbao, Tobias Horn, Agata Horvath, Beata Karpenska, Attila Kovacs, Josef Kreis, Dietrich Leimsner, Ren Leon, Claire Lohr, Ramit Manohar Kal, Rick Marcellus, Martin Matthias, Don Mills, Blair Moe, Gary Mogurodi, Ingvar Nordstrom, Tal Per, Palma Poliak, Mele Posthuma, Lloyd Roden, Adam Roman, Abhishek Sharma, Peter Soter, Luchan Stopp, Andrea Sabot, Jan Takak, Benjamin Timmermans, Chris Von Baal, Eric von Veenendaal, John Versmissen, Karsten Weiss, Robert Workhoven, Paul Weymouth. Certified Tester Advanced Level Test Analyst, CTALTA: Stefan Hohachi, Reto Mueller, Thomas Mueller, Ingvar Nordstrom, Tal Per, Raluca Madalina Popescu, Stuart Reed, Jan Sabak, Hans Schaefer, Marco Sogliani, Yaron Tsuberi, Hans Wieberg, Paul Weymouth, Chris Van Vale, Jurien van der Laar, Stephanie van Dijk, Eric van Veenendaal, Wenqiang Zheng, Debbie Zilberman. Certified Tester, Advanced Level, Test Analyst, CTAL TA. 0. Introduction to this syllabus. 0.1 Purpose of this syllabus. This syllabus forms the basis for the International Software Testing Qualification at the advanced level for the Test Analyst. The ISTQB provides this syllabus as follows. 1. To national boards, to translate into their local language, and to accredit training providers. National boards may adapt the syllabus to their particular language needs and modify the references to adapt to their local publications. 2. To exam boards, to derive examination questions in their local language adapted to the learning objectives for each syllabus. 3. To training providers, to produce courseware and determine appropriate teaching methods. 4. To certification candidates, to prepare for the exam as part of a training course or independently. 5. To the international software and systems engineering community to advance the profession of software and systems testing and as a basis for books and articles. The ISTQB may allow other entities to use this syllabus for other purposes provided they seek and obtain prior written permission. 0.2 The Certified Tester Advanced Level in Software Testing. The advanced level core qualification is comprised of 3 separate syllabi relating to the following roles: Test Manager, Test Analyst, Technical Test Analyst. The ISTQB Advanced Level Overview 2019 is a separate document, ISTQB OView, which includes the following information: business outcomes for each syllabus, matrix showing traceability between business outcomes and learning objectives, summary for each syllabus, relationships between the syllabi. 0.3 Examinable learning objectives and cognitive levels of knowledge. The learning objectives support the business outcomes and are used to create the examination for achieving the Advanced Test Analyst certification. The knowledge levels of the specific learning objectives at K2, K3, and K4 levels are shown at the beginning of each chapter and are classified as follows: K2, Understand, K3, Apply, K4, Analyze. The definitions of all terms listed as keywords just below the chapter headings shall be remembered, K1, even if not explicitly mentioned in the learning objectives. Certified Tester Advanced Level Test Analyst, CTAL-TA. Point 4. The Advanced Level Test Analyst Exam. The Advanced Level Test Analyst exam will be based on this syllabus. Answers to exam questions may require the use of materials based on more than one section of this syllabus. All sections of the syllabus are examinable except for the introduction and the appendices. Standards, books, and other ISTQB syllabi are included as references, but their content is not examinable beyond what is summarized in this syllabus itself from such standards, books, and other ISTQB syllabi. The format of the exam is multiple choice. There are 40 questions. To pass the exam, at least 65% of the total points must be earned. Exams may be taken as part of an accredited training course, or taken independently, e.g. at an exam center or in a public exam. Completion of an accredited training course is not a prerequisite for the exam. Point 5. Entry requirements for the exam. The Certified Tester Foundation Level Certificate shall be obtained before taking the Advanced Level Test Analyst Certification exam. Point 6. Expectations of experience. None of the learning objectives for the Advanced Test Analyst assume that specific experience is available. Point 7. Accreditation of courses. An ISTQB member board may accredit training providers whose course material follows this syllabus. Training providers should obtain accreditation guidelines from the member board or body that performs the accreditation. An accredited course is recognized as conforming to this syllabus and is allowed to have an ISTQB exam as part of the course. Point 8. Level of syllabus detail. The level of detail in this syllabus allows internationally consistent courses and exams. In order to achieve this goal, the syllabus consists of 1. General instructional objectives describing the intention of the advanced level test analyst. 2. A list of items that students must be able to recall. 3. Learning objectives of each knowledge area, describing the cognitive learning outcome to be achieved. 4. A description of the key concepts, including references to sources such as accepted literature or standards. The syllabus content is not a description of the entire knowledge area. It reflects the level of detail to be covered in advanced level training courses. It focuses on material that can apply to all software projects, including agile software development. The syllabus does not contain any specific learning objectives relating to any particular software development lifecycle, SDLC, but it does discuss how these concepts apply in agile software development, other types of iterative and incremental life cycles, and in sequential life cycles. Certified Tester Advanced Level Test Analyst CTAL. 9. How this syllabus is organized. There are 6 chapters with examinable content. The top-level heading of each chapter specifies the minimum time for instruction and exercises for the chapter. Timing is not provided below the chapter level. For accredited training courses, the syllabus requires a minimum of 20 hours and 30 minutes of instruction, distributed across the 6 chapters as follows. 1. Chapter 1. The Test Analyst's Tasks in the Test Process, 150 minutes. 2. Chapter 2. The Test Analyst's Tasks in Risk-Based Testing, 60 minutes. 3. Chapter 3. Test Techniques, 630 minutes. 4. Chapter 4. Testing Software Quality Characteristics, 180 minutes. 5. Chapter 5. Reviews, 120 minutes. 6. Chapter 6. Test Tools and Automation, 90 minutes. Certified Tester Advanced Level Test Analyst CTALTA. 1. The Test Analyst's Tasks in the Test Process, 150 mins. Keywords: Exit Criteria, High-Level Test Case, Low-Level Test Case, Test, Test Analysis, Test Basis, Test Condition, Test Data, Test Design, Test Execution, Test Execution Schedule, Test Implementation, Test Procedure, Test Suite. Learning Objectives for the Test Analyst's Tasks in the Test Process. 1.1. Introduction. No Learning Objectives. 1.2. Testing in the Software Development Lifecycle. TA-1.2.1. K2. Explain how and why the timing and level of involvement for the test analyst varies when working with different software development lifecycle models. 1.3. Test Analysis. TA-1.3.1. K2. Summarize the appropriate tasks for the test analyst when conducting analysis activities. 1.4. Test Design. TA-1.4.1. K2. Explain why test conditions should be understood by the stakeholders. TA-1.4.2. K4. For a given project scenario, select the appropriate design level for test cases, high level or low level. TA-1.4.3. K2. Explain the issues to be considered in test case design. 1.5. Test Implementation. TA-1.5.1. K2. Summarize the appropriate tasks for the test analyst when conducting test implementation activities. 1.6. Test Execution. TA-1.6.1. K2. Summarize the appropriate tasks for the test analyst when conducting test execution activities. Certified Tester Advanced Level Test Analyst CTAL. 1.1 Introduction. In the ISTQB foundation level syllabus, the test process is described as including the following activities: test planning, test monitoring and control, test analysis, test design, test implementation, test execution, test completion. In this advanced level test analyst syllabus, the activities which have particular relevance for the test analyst are considered in more depth. This provides additional refinement of the test process to better fit different software development lifecycle (SDLC) models. Determining the appropriate tests, designing and implementing them, and then executing them are the primary areas of concentration for the test analyst. While it is important to understand the other steps in the test process, the majority of the test analyst's work usually focuses on the following activities: test analysis, test design, test implementation, test execution. The other activities of the test process are adequately described at the foundation level and do not need further elaboration at this level. 1.2 Testing in the software development lifecycle. The overall SDLC should be considered when defining a test strategy. The moment of involvement for the test analyst is different for the various SDLCs. The amount of involvement, time required, information available, and expectations can be quite varied as well. The test analyst must be aware of the types of information to supply to other related organizational roles, such as requirements engineering and management, requirements reviews feedback, project management, schedule input, configuration and change management, results of build verification testing, version control information, software development, notifications of defects found, software maintenance, reports on defects, defect removal efficiency, and confirmation testing, technical support, accurate documentation for workarounds and known issues, production of technical documentation, e.g., database design specifications, test environment documentation, input to these documents as well as technical review of the documents. Test activities must be aligned with the chosen SDLC, whose nature may be sequential, iterative, incremental, or a hybrid of these. For example, in the sequential V model, the test process applied to the system test level could align as follows. System test planning occurs concurrently with project planning, and test monitoring and control continues until test completion. This will influence the schedule inputs provided by the test analyst for project management purposes. Certified Test Analyst Advanced Level Test Analyst CTAL TA. System test analysis and design aligns with documents such as the System Requirement Specification, System and Architectural High-Level Design Specification, and Component Low-Level Design Specification. Implementation of the system test environment might start during system design, though the bulk of it typically would occur concurrently with coding and component testing, with work on system test implementation activities stretching often until just days before the start of system test execution. System test execution begins when the entry criteria are met, or, if necessary, waived, which typically means that at least component testing, and often also component integration testing, have met their exit criteria. System test execution continues until the system test exit criteria are met. System test completion activities occur after the system test exit criteria are met. Iterative and incremental models may not follow the same order of activities and may exclude some activities. For example, an iterative model may utilize a reduced set of test activities for each iteration. Test analysis, design, implementation, and execution may be conducted for each iteration, whereas high-level planning is done at the beginning of the project and completion tasks are done at the end. In agile software development, it is common to use a less formalized process and a much closer working relationship with project stakeholders that allows changes to occur more easily within the project. There may not be a well-defined test analyst role. There is less comprehensive test documentation, and communication is shorter and more frequent. Agile software development involves testing from the outset. This starts from the initiation of the product development, as the developers perform their initial architecture and design work. Reviews may not be formalized, but are continuous as the software evolves. Involvement is expected to be throughout the project, and test analyst tasks are expected to be done by the team. Iterative and incremental models range from agile software development, where there is an expectation for change as the customer requirements evolve, to hybrid models, e.g., iterative/incremental development combined with a V-model approach. In such hybrid models, test analysts should be involved in the planning and design aspects of the sequential activities and then move to a more interactive role during the iterative/incremental activities. Whatever the SDLC being used, test analysts need to understand the expectations for involvement as well as the timing of that involvement. Test analysts provide an effective contribution to software quality by adjusting their activities and their moment of involvement to the specific SDLC rather than sticking to a predefined role model. 1.3. Test analysis. During test planning, the scope of the testing project is defined. During test analysis, test analysts use this scope definition to analyze the test basis, identify defects of various types in the test basis, identify and prioritize test conditions and features to be tested, capture bidirectional traceability between each element of the test basis and the associated test conditions, perform tasks associated with risk-based testing, see Chapter 2. In order for test analysts to proceed effectively with test analysis, the following entry criteria should be:
Certified Tester Advanced Level, Test Analyst, CTAL-TA. There is a body of knowledge, e.g. requirements, user stories, describing the test object that can serve as its test basis. See ISTQB FL SIL sections 1.4.2 and 2.2, or a list of other possible sources of test basis. This test basis has passed review with reasonable results and has been updated as needed after the review. Note that if high-level test cases are to be defined, see section 1.4.1, the test basis may not yet need to be fully defined. In agile software development, this review cycle will be iterative as the user stories are refined at the beginning of each iteration. There is an approved budget and schedule available to accomplish the remaining testing tasks for this test object. Test conditions are typically identified by analysis of the test basis, in conjunction with the test objectives, as defined in test planning. In some situations, where documentation may be old or non-existent, the test conditions may be identified by discussion with relevant stakeholders, e.g. in workshops or during iteration planning. In agile software development, the acceptance criteria, which are defined as part of user stories, are often used as the basis for the test design. While test conditions are usually specific to the item being tested, there are some standard considerations for the test analyst. It is usually advisable to define test conditions at differing levels of detail. Initially, high-level conditions are identified to define general targets for testing, such as functionality of screen X. Subsequently, more detailed conditions are identified as the basis of specific test cases, such as screen X rejects an account number that is 1 digit short of the correct length. Using this type of hierarchical approach to defining test conditions can help to ensure the coverage is sufficient for the high-level items. This approach also allows a test analyst to start working on defining high-level test conditions for user stories that have not yet been refined. If product risks have been defined, then the test conditions that will be necessary to address each product risk should be identified and traced back to that risk item. The application of test techniques, as identified within the test strategy and/or the test plan, can be helpful in test analysis activities and may be used to support the following objectives: identifying test conditions, reducing the likelihood of omitting important test conditions, defining more precise and accurate test conditions, After the test conditions have been identified and refined, review of these conditions with the stakeholders can be conducted to ensure the requirements are clearly understood and that testing is aligned with the goals of the project. At the conclusion of the test analysis activities for a given area, e.g. a specific function, the test analyst should know what specific tests must be designed for that area. 1.4. Test design. Still adhering to the scope determined during test planning, the test process continues as the test analyst designs the tests which will be implemented and executed. Test design includes the following: determining in which test areas low-level or high-level test cases are appropriate. Determining the test techniques that will enable the necessary coverage to be achieved. The techniques that may be used are established during test planning. Using test techniques to design test cases and sets of test cases that cover the identified test conditions. Identifying necessary test data to support test conditions and test cases.
Certified Test Analyst, Advanced Level, Test Analyst, CTAL. Capturing bidirectional traceability, e.g., between the test basis, test conditions, and test cases. Prioritization criteria identified during risk analysis and test planning should be applied throughout the process, from analysis and design to implementation and execution. Depending on the types of tests being designed, one of the entry criteria for test design may be the availability of tools that will be used during the design work. During test design, the test analyst must consider at least the following. Some test items are better addressed by defining only the test conditions rather than going further into the definition of test scripts, which give the sequence of instructions required to execute a test. In this case, the test conditions should be defined to be used as a guide for unscripted testing. The pass-fail criteria should be clearly identified. Tests should be designed to be understandable by other testers, not just the author. If the author is not the person who executes the test, other testers will need to read and understand previously specified tests in order to understand the test objectives and the relative importance of the test. Tests must also be understandable for other stakeholders, such as developers, who may review the tests, and auditors, who may have to approve the tests. Tests should cover all types of interaction with the test object and should not be restricted to the interactions of people through the user visible interface. They may also include, for example, interaction with other systems and technical or physical events. See IREB CPR. Tests should be designed to test the interfaces between the various test items as well as the behaviors of the items themselves. Test design effort must be prioritized and balanced to align with the risk levels and business value. 1.4.1 Low-level and high-level test cases. One of the jobs of the test analyst is to determine the best design level of test cases for a given situation. Low-level and high-level test cases are covered in ISTQB FLS. Some of the advantages and disadvantages of using these are described in the following lists. Low-level test cases provide the following advantages. Inexperienced testing staff can rely on detailed information provided within the project. Low-level test cases provide all the specific information and procedures needed for the tester to execute the test case, including any data requirements. Tests may be rerun by different testers and should achieve the same test results. Non-obvious defects in the test basis can be revealed. The level of detail enables an independent verification of the tests, such as audits, if required. Time spent on automated test case implementation can be reduced. Low-level test cases have the following disadvantages. They may require a significant amount of effort, both for creation and maintenance. They tend to limit tester ingenuity during execution. They require that the test basis be well defined. Their traceability to test conditions may take more effort than with high-level test cases. Certified Test Analyst, Advanced Level, Test Analyst, CTAL-TA. High-level test cases provide the following advantages. They give guidelines for what should be tested and allow the test analyst to vary the actual data or even the procedure that is followed when executing the test. They may provide better risk coverage than low-level test cases because they will vary somewhat each time they are executed. They can be defined early in the requirements process. They make use of the test analyst's experience with both testing and the test object when the test is executed. They can be defined when no detailed and formal documentation is required. They are better suited for reuse in different test cycles when different test data can be used. High-level test cases have the following disadvantages. They are less reproducible, making verification difficult. This is because they lack the detailed description found in low-level test cases. More experienced testing staff may be needed to execute them. When automating on the basis of high-level test cases, the lack of details may result in validating the wrong actual results or missing items that should be validated. High-level test cases may be used to develop low-level test cases when the requirements become more defined and stable. In this case, the test case creation is done sequentially, flowing from high-level to low-level, with only the low-level test cases being used for execution. 1.4.2 Design of test cases. Test cases are designed by the stepwise elaboration and refinement of the identified test conditions using test techniques. See Chapter 3. Test cases should be repeatable, verifiable, and traceable back to the test basis, e.g. requirements. Test design includes the identification of the following. Objective, i.e. the observable, measurable objective of test execution. Preconditions, such as either project or localized test environment requirements and the plans for their delivery, state of the system prior to test execution, etc. Test data requirements, both input data for the test case as well as data that must exist in the system for the test case to be executed. Expected results with explicit pass-fail criteria. Post-conditions, such as affected data, state of the system after test execution, triggers for subsequent processing, etc. A particular challenge can be the definition of the expected result of a test. Computing this manually is often tedious and error-prone. If possible, it might be preferable to find or create an automated test oracle. In identifying the expected result, testers are concerned not only with outputs on the screen, but also with data and environmental post-conditions. If the test basis is clearly defined, identifying the correct result, theoretically, should be simple. However, test basis documentation might be vague, contradictory, lacking coverage of key areas, or missing entirely. In such cases, a test analyst must have subject matter expertise or have access to it. Also, even when the test basis is well specified, complex interactions of complex stimuli and responses can make the definition of the expected results difficult. Therefore, a test oracle is essential. In agile software development, the test oracle might be the product owner. Test case execution without any way to determine correctness of actual results might have a very low added value or benefit, often generating invalid test reports or false confidence in the system.
Certified Test Analyst Advanced Level Test Analyst, CTALTA. The activities described above may be applied to all test levels, though the test basis will vary. When analyzing and designing tests, it is important to remember the target level for the test, as well as the objective of the test. This helps to determine the level of detail required, as well as any tools that may be needed, e.g. drivers and stubs at the component test level. During the development of test conditions and test cases, some amount of documentation is typically created, resulting in test work products. In practice, the extent to which test work products are documented varies considerably. This can be affected by any of the following. Project risks, what must not be documented. The added value which the documentation brings to the project. Standards to be followed and/or regulations to be met. SDLC or approach used, e.g. an agile approach aims for just enough documentation.
The requirement for traceability from the test basis through test analysis and design. Depending on the scope of the testing, test analysis and design address the quality characteristics for the test object. The ISO 2510 standard, ISO 2501, provides a useful reference. When testing hardware-software systems, additional characteristics may apply. The activities of test analysis and test design may be enhanced by intertwining them with reviews and static analysis. In fact, conducting the test analysis and test design are often a form of static testing, because problems may be found in the test basis documents during this activity. Test analysis and test design, based on the requirement specification, is an excellent way to prepare for a requirements review meeting. Reading the requirements to use them for creating tests requires understanding the requirement and being able to determine a way to assess fulfillment of the requirement. This activity often uncovers missing requirements, requirements that are not clear, are untestable, or do not have defined acceptance criteria. Similarly, test work products such as test cases, risk analyses, and test plans can be subjected to reviews. If testing requires infrastructure that is not readily available, the test analyst should define the detailed test infrastructure requirements during test design. Should these requirements not be completed in time, test implementation will be at risk of overrun due to unexpected time and effort. It must be remembered that test infrastructure includes more than test objects and testware. For example, the infrastructure requirements may include rooms, equipment, personnel, software, tools, peripherals, communications equipment, user authorizations, and all other items required to run the tests. The exit criteria for test analysis and test design will vary depending on the project parameters, but all items discussed in these two sections should be considered for inclusion in the defined exit criteria. It is important that the exit criteria are measurable and that all the information required for the subsequent steps has been provided and all necessary preparation has been performed. 1.5. Test implementation. Test implementation prepares the testware needed for test execution based on test analysis and design. It includes the following activities: developing test procedures and, potentially, creating automated test scripts. Organizing test procedures and automated test scripts, if there are any, into test suites to be executed in a specific test run. Consulting the test manager in prioritizing the test cases and test suites to be executed. Creating a test execution schedule, including resource allocation, to enable test execution to begin. See ISTQB FL/SY, Section 5.2.4. Finalizing preparation of test data and test environments. Certified Tester Advanced Level, Test Analyst, CTALTA. Updating the traceability between the test basis and testware, such as test conditions, test cases, test procedures, test scripts, and test suites. During test implementation, test analysts identify an efficient execution order of test cases and create test procedures. Defining the test procedures requires carefully identifying constraints and dependencies that might influence the test execution sequence. Test procedures document any initial preconditions, e.g., loading of test data from a data repository, and any activities following execution, e.g., resetting the system status. Test analysts identify test procedures and automated test scripts that can be grouped, e.g., they all relate to the testing of a particular high-level business process, and organize them into test suites. This enables related test cases to be executed together. Test analysts arrange test suites within a test execution schedule in a way that results in efficient test execution. If a risk-based test strategy is being used, the risk level will be the primary consideration in determining the execution order for the test cases. There may be other factors that determine test case execution order, such as the availability of the right people, equipment, data, and the functionality to be tested. It is not unusual for code to be released in sections, and the test effort has to be coordinated with the sequence in which the software becomes available for testing. Particularly in iterative and incremental development models, it is important for the test analyst to coordinate with the development team to ensure that the software will be released for testing in a testable order. The level of detail and associated complexity for work done during test implementation may be influenced by the detail of the test conditions and test cases. In some cases, regulatory rules apply, and test work products should provide evidence of compliance to applicable standards such as the United States Standard DO-178C, in Europe ED-12C, RTCA DO-178C/ED-12C. As specified above, test data is needed for most testing, and in some cases, these sets of data can be quite large. During implementation, test analysts create input and environment data to load into databases and other such repositories. This data must be fit for purpose to enable detection of defects. Test analysts may also create data to be used with data-driven and keyword-driven testing, see Section 6.2, as well as for manual testing. Test implementation is also concerned with the test environments. During this activity, the environments should be fully set up and verified prior to test execution. A fit-for-purpose test environment is essential, i.e., the test environment should be capable of enabling the exposure of the defects present during controlled testing, operate normally when failures are not occurring, and adequately replicate, if required, the production or end-user environment for higher test levels. Test environment changes may be necessary during test execution, depending on anticipated changes, test results, or other considerations. If environment changes do occur during execution, it is important to assess the impact of the changes to tests that have already been run. During test implementation, test analysts should check that those responsible for the creation and maintenance of the test environment are known and available, and that all the testware and test support tools and associated processes are ready for use. This includes configuration management, defect management, and test logging and management. In addition, test analysts must verify the procedures that gather data for evaluating current status against exit criteria and test results reporting. It is wise to use a balanced approach to test implementation as determined during test planning.
For example, risk-based analytical test strategies are often blended with reactive test strategies. In this case, Certified Tester Advanced Level Test Analyst CTAL. Some percentage of the test implementation effort is allocated to testing which does not follow predetermined scripts, unscripted. Unscripted testing should not be random or aimless, as this can be unpredictable in duration and coverage and give a low yield in defects. Rather, it should be conducted in time-boxed sessions, each given initial direction by a test charter, but with the freedom to depart from the charter's prescriptions if potentially more productive test opportunities are discovered in the course of the session. Over the years, testers have developed a variety of experience-based test techniques, such as attacks, Whitaker 03, error guessing, Myers 11, and exploratory testing, Whitaker 09. Test analysis, test design, and test implementation still occur, but they take place primarily during test execution. When following such reactive test strategies, the results of each test influence the analysis, design, and implementation of the subsequent tests. While these strategies are lightweight and often effective at finding defects, there are some drawbacks, including the following. Expertise from the test analyst is required. Duration can be difficult to predict. Coverage can be difficult to track. Repeatability can be lost without good documentation or tool support. 1.6. Test execution. Test execution is conducted according to the test execution schedule and includes the following tasks. See ISTQB FLSYL. Executing manual tests, including exploratory testing. Executing automated tests. Comparing actual results with expected results. Analyzing anomalies to establish their likely causes, reporting defects based on the failures observed, logging the actual results of test execution, updating the traceability between the test basis and testware to consider test results, executing regression tests. The test execution tasks listed above may be conducted by either the tester or the test analyst. The following are typical additional tasks which may be performed by the test analyst. Recognizing defect clusters which may indicate the need for more testing of a particular part of the test object. Making suggestions for future exploratory testing sessions based on the findings from exploratory testing. Identifying new risks from information obtained when performing test execution tasks. Making suggestions for improving any of the work products from the test implementation activity, e.g., improvements to test procedures.
Certified Test Analyst Advanced Level, Test Analyst, CTAL. 2. The Test Analyst's tasks in risk-based testing, 60 minutes. Keywords: product risk, risk identification, risk mitigation, risk-based testing. Learning objectives for the test analyst's tasks in risk-based testing. The test analyst's tasks in risk-based testing. TA-2.1.1. K3. For a given situation, participate in risk identification, perform risk assessment, and propose appropriate risk mitigation. Certified Tester Advanced Level, Test Analyst, CTAL-T. 2.1 Introduction. Test managers often have overall responsibility for establishing and managing a risk-based test strategy. They will usually request the involvement of a test analyst to ensure the risk-based approach is implemented correctly. Test analysts should be actively involved in the following risk-based testing tasks: risk identification, risk assessment, risk mitigation. These tasks are performed iteratively throughout the SDLC to deal with emerging risks, changing priorities, and to regularly evaluate and communicate risk status. See Veenendaal 1.2 and Black 02 for further details. In Agile software development, the three tasks are often combined in a so-called risk session, with focus on either an iteration or a release. Test analysts should work within the risk-based test framework established for the project by the test manager. They should contribute their knowledge of the business domain risks that are inherent in the project, such as risks related to safety, business and economic concerns, and political factors, among others. 2.2 Risk Identification. By calling on the broadest possible sample of stakeholders, the risk identification process is most likely to detect the largest possible number of significant risks. Test analysts often possess unique knowledge regarding the particular business domain of the system under test. This means they are particularly well suited to the following tasks: conducting expert interviews with the domain experts and users, conducting independent assessments, using risk templates, participating in risk workshops, participating in brainstorming sessions with potential and current users, defining testing checklists, calling on past experience with similar systems or projects. In particular, test analysts should work closely with the users and other domain experts, e.g., requirement engineers, business analysts, to determine the areas of business risk that should be addressed during testing. In Agile software development, this close relationship with stakeholders enables risk identification to be conducted on a regular basis, such as during iteration planning meetings. Sample risks that might be identified in a project include issues with functional correctness, e.g., incorrect calculations, usability issues, e.g., insufficient keyboard shortcuts, portability issues, e.g., inability to install an application on particular platforms. 2.3 Risk Assessment. While risk identification is about identifying as many pertinent risks as possible, risk assessment is the study of these identified risks, specifically categorizing each risk and determining its risk level. Certified Tester Advanced Level Test Analyst, CTALTA. Determining the risk level typically involves assessing for each risk item the risk likelihood and the risk impact. The risk likelihood is usually interpreted as the likelihood that the potential problem can exist in the system under test and will be observed when the system is in production. Technical test analysts should contribute to finding and understanding the potential likelihood for each risk item, whereas test analysts contribute to understanding the potential business impact of the problem should it occur. In agile software development, this role-based distinction may be less strong. The risk impact is often interpreted as the severity of the effect on the users, customers, or other stakeholders. In other words, it arises from business risk. Test analysts should contribute to identifying and assessing the potential business domain or user impact for each risk item. Factors influencing business risk include the following: frequency of use of the affected feature, business loss, financial damage, ecological or social losses or liability, civil or criminal legal sanctions, safety concerns, fines, loss of license, lack of reasonable workarounds if people cannot work anymore, visibility of the feature, visibility of failure leading to negative publicity and potential image damage, loss of customers. Given the available risk information, test analysts need to establish the levels of business risk, according to the guidelines provided by a test manager. These could be classified using an ordinal scale, actual numeric or low, medium, high, or traffic signal colors. Once the risk likelihood and risk impact have been assigned, test managers use these values to determine the risk level for each risk item. That risk level is then used to prioritize the risk mitigation activities. 2.4. Risk mitigation. During the project, test analysts should seek to do the following: reduce product risk by designing effective test cases that demonstrate unambiguously whether tests pass or fail, and by participating in reviews of software work products such as requirements, designs, and user documentation. Implement appropriate risk mitigation activities identified in the test strategy and test plan, e.g., test a particularly high-risk business process using particular test techniques. Re-evaluate known risks based on additional information gathered as the project unfolds, adjusting risk likelihood, risk impact, or both as appropriate. Identify new risks from information obtained during testing. When one is talking about a product risk, then testing makes an essential contribution to mitigating such risks. By finding defects, testers reduce risk by providing awareness of the defects and opportunities to deal with the defects before release. If the testers find no defects, testing then reduces risk by providing evidence that, under certain conditions, i.e., the conditions tested, the system operates correctly. Test analysts help to determine risk mitigation options by investigating opportunities for gathering accurate test data, creating and testing realistic user scenarios, and conducting or overseeing usability studies, among others. Certified Tester Advanced Level, Test Analyst. Test Analyst, CTAL, TA. 2.4.1. Prioritizing the tests. The level of risk is also used to prioritize tests. A test analyst might determine that there is a high risk in the area of transactional accuracy in an accounting system. As a result, to mitigate the risk, the tester may work with other business domain experts to gather a strong set of sample data that can be processed and verified for accuracy. Similarly, a test analyst might determine that usability issues are a significant risk for a new test object. Rather than wait for a user acceptance test to discover any issues, the test analyst might prioritize an early usability test based on a prototype to help identify and resolve usability design problems early before the user acceptance test. This prioritization must be considered as early as possible in the planning stages, so that the schedule can accommodate the necessary testing at the necessary time. In some cases, all of the highest risk tests are run before any lower risk tests, and tests are run in strict risk order, called depth first. In other cases, a sampling approach is used to select a sample of tests across all the identified risk areas using risk level to weight the selection, while at the same time ensuring coverage of every risk at least once, called breadth first. Whether risk-based testing proceeds depth first or breadth first, it is possible that the time allocated for testing might be consumed without all tests being run. Risk-based testing allows testers to report to management in terms of the remaining level of risk at this point, and allows management to decide whether to extend testing or to transfer the remaining risk onto the users, customers, help desk, technical support, and/or operational staff. 2.4.2 Adjusting testing for future test cycles. Risk assessment is not a one-time activity performed before the start of test implementation. It is a continuous process. Each future planned test cycle should be subjected to new risk analysis to take into account such factors. Any new or significantly changed product risks. Unstable or failure-prone areas discovered during the testing. Risks from fixed defects. Typical defects found during testing. Under-tested areas, low requirements coverage.
Certified Tester Advanced Level Test Analyst, CTAL TA. 3. Test Techniques, 630 minutes. Keywords: Black Box Test Technique, Boundary Value Analysis, Checklist-Based Testing, Classification Tree Technique, Decision Table Testing, Defect Taxonomy, Defect-Based Test Technique, Equivalence Partitioning, Error Guessing, Experience-Based Testing, Experience-Based Test Technique, Exploratory Testing, Pairwise Testing, State Transition Testing, Test Charter, Use Case Testing. Learning Objectives for Test Techniques. 3.1 Introduction. No learning objectives. 3.2 Black Box Test Techniques. TA-3.2.1 K4 Analyze a given specification item S and design test cases by applying equivalence partitioning. TA-3.2.2 K4 Analyze a given specification item S and design test cases by applying boundary value analysis. TA-3.2.3 K4 Analyze a given specification item S and design test cases by applying decision table testing. TA-3.2.4 K4 Analyze a given specification item S and design test cases by applying state transition testing. TA-3.2.5 K2 Explain how classification tree diagrams support test techniques. TA-3.2.6 K4 Analyze a given specification item S and design test cases by applying pairwise testing. TA-3.2.7 K4 Analyze a specification item S and design test cases by applying use case testing. TA-3.2.8 K4 Analyze a system or its requirement specification in order to determine likely types of defects to be found and select the appropriate black box test techniques. 3.3 Experience-based test techniques. TA-3.3.1 K2 Explain the principles of experience-based test techniques and the benefits and drawbacks compared to black box and defect-based test techniques. TA-3.3.2 K3 Identify exploratory tests from a given scenario. TA-3.3.3 K2 Describe the application of defect-based test techniques and differentiate their use from black box test techniques. 3.4 Applying the most appropriate test techniques. TA-3.4.1 K4 For a given project situation, determine which black box or experience-based test techniques should be applied to achieve specific goals.
Certified Tester Advanced Level Test Analyst, CTAL TA. 3.1 Introduction. The test techniques considered in this chapter are divided into the following categories. Black box. Experience-based. These techniques are complementary and may be used as appropriate for any given test activity, regardless of which test level is being performed. Note that both categories of techniques can be used to test functional and non-functional quality characteristics. Testing software characteristics is discussed in the next chapter. The test techniques discussed in these sections may focus primarily on determining optimal test data, e.g., from equivalence partitions, or deriving test procedures, e.g., from state models. It is common to combine techniques to create complete test cases. 3.2 Black box test techniques. Black box test techniques are introduced in the ISTQB Foundation Level Syllabus, ISTQB FL/SYL. Common features of black box test techniques include models, e.g., state transition diagrams and decision tables, are created during test design according to the test technique. Test conditions are derived systematically from these models. Test techniques generally provide coverage criteria, which can be used for measuring test design and test execution activities. Completely fulfilling the coverage criteria does not mean that the entire set of tests is complete, but rather that the model no longer suggests any additional tests to increase coverage based on that technique. Black box testing is usually based on some form of specification documentation, such as a system requirement specification or user stories. Since the specification documentation should describe system behavior, particularly in the area of functionality, deriving tests from the requirements is often part of testing the behavior of the system. In some cases, there may be no specification documentation, but there are implied requirements, such as replacing the functionality of a legacy system. There are a number of black box test techniques. These techniques target different types of software and scenarios. The sections below show the applicability for each technique, some limitations and difficulties that the test analyst may experience, the method by which coverage is measured, and the types of defects that are targeted. Please refer to ISO 29194, Bath 14, Baser 95, Black 07, Black 09, Copeland 04, Craig 02, Forgács 19, Kuman 06, and Myers 11 for further details. 3.2.1 Equivalence partitioning. Equivalence partitioning, EP, is a technique used to reduce the number of test cases required to effectively test the handling of inputs, outputs, internal values, and time-related values. Partitioning is used to create equivalence partitions, often called equivalence classes, which are created from sets of values that are required to be processed in the same manner. By selecting one representative value from a partition, coverage for all the items in the same partition is assumed. Usually, several parameters determine the behavior of the test object. When combining the equivalence,
Certified Tester Advanced Level, Test Analyst, CTAL, TA. Applicability. This technique is applicable at any test level and is appropriate when all the members of a set of values to be tested are expected to be handled in the same way, and where the sets of values used by the application do not interact. An equivalence partition can be any non-empty set of values, e.g., ordered, unordered, discrete, continuous, infinite, finite, or even a singleton. The selection of sets of values is applicable to valid and invalid partitions, i.e., partitions containing values that should be considered invalid for the software under test. EP is strongest when used in combination with boundary value analysis, which expands the test values to include those on the edges of the partitions. EP, using values from the valid partitions, is a commonly used technique for smoke testing a new build or a new release, as it quickly determines if basic functionality is working. Limitations/difficulties. If the assumption is incorrect and the values in the partition are not handled in exactly the same way,
This technique may miss defects. It is also important to select the partitions carefully. For example, an input field that accepts positive and negative numbers might be better tested as two valid partitions, one for the positive numbers and one for the negative numbers, because of the likelihood of different handling. Depending on whether or not 0 is allowed, this could become another partition. It is important for a test analyst to understand the underlying processing in order to determine the best partitioning of the values. This may require support in understanding code design. The test analyst should also take into account possible dependencies between equivalence partitions of different parameters. For example, in a flight reservation system, the parameter accompanying adult may only be used in combination with the age class child. Coverage. Coverage is determined by taking the number of partitions for which a value has been tested and dividing that number by the number of partitions that have been identified. EP coverage is then stated as a percentage. Using multiple values for a single partition does not increase the coverage percentage. If the behavior of the test object depends on a single parameter, each equivalence partition, whether valid or invalid, should be covered at least once. In the case of more than one parameter, the test analyst should select a simple or combinatorial coverage type depending on the risk. Offute 16. Differentiating between combinations containing only valid partitions and combinations containing one or more invalid partitions is therefore essential. Regarding the combinations with only valid equivalence partitions, the minimum requirement is a simple coverage of all valid partitions over all parameters. The minimum number of test cases needed in such a test suite equals the greatest number of valid partitions of a parameter, assuming the parameters are independent on each other. More thorough coverage types related to combinatorial techniques include the pairwise coverage, see section 3.2.6, or the full coverage of any combination of valid partitions. Invalid equivalence partitions should be tested at least individually, i.e., in combination with valid partitions for the other parameters in order to avoid defect masking. So, each invalid partition contributes one test case to the test suite for simple coverage. In case of high risk, further combinations may be added to the test suite, e.g., consisting of only invalid partitions or of pairs of invalid partitions. Types of defects. A test analyst uses this technique to find defects in the handling of various data values. Certified Tester Advanced Level, Test Analyst, CTAL TA. 3.2.2 Boundary Value Analysis. Boundary Value Analysis, BVA, is used to test the proper handling of values that exist on the boundaries of ordered equivalence partitions. Two approaches to BVA are in common use: two-value boundary or three-value boundary testing. With two-value boundary testing, the boundary value on the boundary and the value that is just outside the boundary by the smallest possible increment based on the required accuracy are used. For example, for amounts in a currency which has two decimal places, if the partition included the values from 1 to 10, the two-value test values for the upper boundary would be 10 and 10.01. The lower boundary test values would be 1 and 0.99. The boundaries are defined by the maximum and minimum values in the defined equivalence partition. For three-value boundary testing, the values before, on, and over the boundary are used. In the previous example, the upper boundary tests would include 9.99, 10, and 10.01. The lower boundary tests would include 0.99, 1, and 1.01. The decision regarding whether to use two-value or three-value boundary testing should be based on the risk associated with the item being tested, with the three-value boundary approach being used for the higher risk items. Applicability. This technique is applicable at any test level and is appropriate when ordered equivalence partitions exist. For this reason, the BVA technique is often conducted together with the EP technique. Ordered equivalence partitions are required because of the concept of being on and off the boundary. For example, a range of numbers is an ordered partition. A partition that consists of some text strings may be ordered too, e.g. by their lexicographic order. But if the ordering is not relevant from the business or technical point of view, then boundary values should not be in focus. In addition to number ranges, partitions for which boundary value analysis can be applied include numeric attributes of non-numeric variables, e.g. length, the number of loop execution cycles, including loops in state transition diagrams, the number of iteration elements in stored data structures, such as arrays, the size of physical objects, e.g. memory, the duration of activities. Limitations/difficulties. Because the accuracy of this technique depends on the accurate identification of the equivalence partitions in order to correctly identify the boundaries, it is subject to the same limitations and difficulties as EP. The test analyst should also be aware of the precision in the valid and invalid values to be able to accurately determine the values to be tested. Only ordered partitions can be used for boundary value analysis, but this is not limited to a range of valid inputs. For example, when testing for the number of cells supported by a spreadsheet, there is a partition that contains the number of cells up to and including the maximum allowed cells, the boundary, and another partition that begins with one cell over the maximum, over the boundary. Coverage. Coverage is determined by taking the number of boundary conditions that are tested and dividing that by the number of identified boundary conditions, either using the 2-value or 3-value method. The coverage is stated as a percentage. Similar to equivalence classes, in the case of multiple parameters, the test analyst should choose a simple or combinatorial coverage type, depending on the risk. Types of defects. Boundary value analysis reliably finds displacement or omission of boundaries, and may find cases of extra boundaries. This technique finds defects regarding the handling of the boundary values, particularly errors with less than and greater than logic, i.e. displacement. It can also be used to find Certified Tester Advanced Level Test Analyst, CTAL. 3.2.3 Decision Table Testing. A decision table is a tabular representation of a set of conditions and related actions, expressed as rules, indicating which action shall occur for which set of condition values. OMG-DMN. Test analysts can use decision tables to analyze the rules which apply to the software under test and design tests to cover those rules. Conditions and the resulting actions of the test object form the rows of the decision table, usually with the conditions at the top and the actions at the bottom. The first column of the table contains the descriptions of the conditions and actions respectively. The following columns, called the rules, contain the condition values and corresponding action values respectively. Decision tables in which conditions are Boolean with simple values, true and false, are called limited entry decision tables. An example for such a condition is user's income less than 1,000. Extended entry decision tables allow for conditions having multiple values which may represent discrete elements or sets of elements. For example, a condition user's income may take one of 3 possible values: lower than 1,000, between 1,000 and 2,000, and more than 2,000. Simple actions take Boolean values true and false, e.g., the action admitted discount equals 20% takes the values true, denoted by X if the action should occur, and false, denoted by minus if not. Just like with conditions, actions may also take values from other domains. For example, an action admitted discount may take one of 5 possible values: 0%, 10%, 20%, 35%, and 50%. Decision table testing starts with designing decision tables based on the specification. Rules containing infeasible combinations of condition values are excluded or marked as infeasible. Next, the test analyst should review the decision tables with the other stakeholders. The test analyst should ensure the rules within the table are consistent, i.e., the rules do not overlap, complete, i.e., they contain a rule for each feasible combination of condition values, and correct, i.e., they model the intended behavior. The basic principle in decision table testing is that the rules form the test conditions. When designing a test case to cover a given rule, the test analyst should be aware that the inputs of the test case might be different parameters than in the conditions of the decision table. For example, the true value of the condition age greater than 18 may require the tester to calculate the age from the input parameters birth date and current date. Similarly, the expected results of the test case may be indirect consequences of the actions of the decision table. After the decision table is ready, the rules need to be implemented as test cases by selecting test input values and expected results that fulfill the conditions and actions. Collapsed decision tables. When trying to test every possible input combination according to the conditions, decision tables can become very large. A complete limited entry decision table with n conditions has 2n rules. A technique of systematically reducing the number of combinations is called collapsed decision table testing, Moseley 93. When this technique is used, a group of rules with the same set of actions can be collapsed to one rule if, within this group, some conditions are not relevant for the action, and all the other conditions remain unchanged. In this resulting rule, the values of the irrelevant conditions are denoted as don't care, usually marked with a dash. For conditions with don't care values, the test analyst may specify arbitrary valid values for test implementation. Another case for collapsing rules is when a condition value is not applicable in combination with some other condition values, or when two or more conditions have conflicting values. For example, Certified Tester Advanced Level Test Analyst, CTAL TA. Decision table for card payments. If the condition card is valid is false, the condition PIN code is correct is not applicable. Collapsed decision tables may have far fewer rules than full decision tables, which results in a lower number of test cases and less effort. If a given rule has don't care entries and only one test case covers this rule, only one of several possible values of the condition will be tested for that rule, so a defect involving other values may remain undetected. Hence, for high risk levels, in alignment with the test manager, the test analyst should define separate rules for each feasible combination of the single condition values rather than collapsing the decision table. Applicability. Decision table testing is commonly applied to integration, system, and acceptance test levels. It may also be applicable to component testing when a component is responsible for a set of decision logic. This technique is particularly useful when the test object is specified in the form of flowcharts or tables of business rules. Decision tables are also a requirements definition technique, and sometimes requirement specifications may already be defined in this format. The test analyst should still participate in reviewing the decision tables and analyze them before starting test design. Limitations/difficulties. When considering combinations of conditions, finding all the interacting conditions can be challenging, particularly when requirements are not well defined or not documented at all. Care must be taken when selecting the conditions considered in a decision table so that the number of combinations of those conditions remains manageable. In the worst case, the number of rules will grow exponentially. Coverage. The common coverage standard for this technique is to cover each rule of the decision table with one test case. The coverage is measured as the number of rules covered by the test suite divided by the total number of feasible rules, expressed as a percentage. Boundary value analysis and equivalence partitioning can be combined with the decision table technique, especially in the case of extended entry decision tables. If conditions contain equivalence partitions that are ordered, the boundary values may be used as additional entries leading to additional rules and test cases. Types of defects. Typical defects include incorrect logic-related processing based on particular combinations of conditions, resulting in unexpected results. During the creation of the decision tables, defects may be found in the specification document. It is not unusual to prepare a set of conditions and determine that the expected result is unspecified for one or more rules. The most common types of defects are omissions of actions, i.e., there is no information regarding what should actually happen in a certain situation, and contradictions. 3.2.4 State Transition Testing. State transition testing is used to test the ability of the test object to enter and exit from defined states via valid transitions, as well as to try entering invalid states or covering invalid transitions. Events cause the test object to transition from state to state and to perform actions. Events may be qualified by conditions, sometimes called guard conditions or transition guards, which influence the transition path to be taken. For example, a login event with a valid username/password combination will result in a
Certified Tester Advanced Level Test Analyst, CTAL. Transition diagram or in a state transition table, which may also include potential invalid transitions between states. Applicability. State transition testing is applicable for any software that has defined states and has events that will cause the transitions between those states, e.g., changing screens. State transition testing can be used at any test level. Embedded software, web software, and any type of transactional software are good candidates for this type of testing. Control systems, e.g., traffic light controllers, are also good candidates for this type of testing. Limitations/difficulties. Determining the states is often the most difficult part of defining the state transition diagram or state transition table. When the test object has a user interface, the various screens that are displayed for the user are often represented by states. For embedded software, the states may be dependent upon the states of the hardware. Besides the states themselves, the basic unit of state transition testing is the individual transition. Simply testing all single transitions will find some kinds of state transition defects, but more may be found by testing sequences of transitions. A single transition is called a zero switch. A sequence of 2 successive transitions is called a 1 switch. A sequence of 3 successive transitions is called a 2 switch, and so forth. In general, an N switch represents N plus 1 successive transitions. With N increasing, the number of N switches grows very quickly, making it difficult to achieve N switch coverage with a reasonable, small number of tests. Coverage. As with other types of test techniques, there is a hierarchy of levels of coverage. The minimum acceptable degree of coverage is to have visited every state and traversed every transition at least once. 100% transition coverage, also known as 100% zero-switch coverage, will guarantee that every state is visited and every transition is traversed, unless the system design or the state transition model, diagram, or table is defective. Depending on the relationships between states and transitions, it may be necessary to traverse some transitions more than once in order to execute other transitions a single time. The term N-switch coverage relates to the number of switches covered of length N plus 1 as a percentage of the total number of switches of that length. For example, achieving 100% one-switch coverage requires that every valid sequence of 2 successive transitions has been tested at least once. This testing may trigger some types of failures that 100% zero-switch coverage would miss. Round-trip coverage applies to situations in which sequences of transitions form loops. 100% round-trip coverage is achieved when all loops from any state back to the same state have been tested for all states at which loops begin and end. This loop cannot contain more than one occurrence of any particular state except the initial final one, Offutt 1.6. For any of these approaches, an even higher degree of coverage will attempt to include all invalid transitions identified in a state transition table. Coverage requirements for state transition testing must identify whether invalid transitions are included. Designing test cases to achieve the desired coverage is supported by the state transition diagram or the state transition table for the particular test object. This information may also be represented in a table that shows the N-switch transitions for a particular value of N, black 09. A manual procedure may be applied for identifying the items to be covered, e.g., transitions, states, or
Certified Tester Advanced Level, Test Analyst, CTAL. Use a pen or pencil to mark up the items covered until the required coverage is shown. This approach would become too time-consuming for more complex state transition diagrams and state transition tables. A tool should therefore be used to support state transition testing. Types of defects. Typical defects include the following. See also Baser 95. Incorrect event types or values. Incorrect action types or values. Incorrect initial state. Inability to reach some exit states. Inability to enter required states. Extra, unnecessary states. Inability to execute some valid transitions correctly. Ability to execute invalid transitions. Wrong guard conditions. During the creation of the state transition model, defects may be found in the specification document. The most common types of defects are omissions, i.e., there is no information regarding what should actually happen in a certain situation, and contradictions. 3.2.5 Classification Tree Technique. Classification trees support certain black box test techniques by enabling a graphical representation of the data space to be created, which applies to the test object. The data is organized into classifications and classes as follows. Classifications. These represent parameters within the data space for the test object, such as input parameters, which can further contain environment states and preconditions, and output parameters. For example, if an application can be configured many different ways, the classifications might include client, browser, language, and operating system. Classes. Each classification can have any number of classes and subclasses, describing the occurrence of the parameter. Each class, or equivalence partition, is a specific value within a classification. In the above example, the language classification might include equivalence partitions for English, French, and Spanish. Classification trees allow the test analysts to enter combinations as they see fit. This includes, for example, pairwise combinations, see section 3.26, three-wise combinations, and single-wise. Additional information regarding the use of the classification tree technique is provided in Bath 14 and Black 09. Applicability. The creation of a classification tree helps a test analyst to identify parameters, classifications, and their equivalence partitions, classes, which are of interest. Further analysis of the classification tree diagram enables possible boundary values to be identified and certain combinations of inputs to be identified which are either of particular interest or may be discounted, e.g., because they are incompatible. The resulting classification tree may then be used to support equivalence partitioning, boundary value analysis, or pairwise testing. See section 3.26. Limitations/difficulties. As the quantity of classifications and/or classes increases, the diagram becomes larger and less easy. Certified Tester Advanced Level Test Analyst, CTAL. Combinations. Test analysts must supply the results for each test combination to create complete test cases. Coverage. Test cases may be designed to achieve, for example, minimum class coverage, i.e., all values in a classification tested at least once. The test analyst may also decide to cover pairwise combinations or use other types of combinatorial testing, e.g., three-wise. Types of defects. The types of defects found depend on the techniques which the classification trees support, i.e., equivalence partitioning, boundary value analysis, or pairwise testing. 3.2.6 Pairwise testing. Pairwise testing is used when testing software in which several input parameters, each with several possible values, must be tested in combination, giving rise to more combinations than are feasible to test in the time allowed. The input parameters may be independent in the sense that any option for any factor, i.e., any selected value for any one input parameter, can be combined with any option for any other factor. However, it is not always the case. See a note on feature models below. The combination of a specific parameter, variable or factor, with a specific value of that parameter is called a parameter value pair. E.g., if color is a parameter with 7 permitted values, including red, then color equals red could be a parameter value pair. Pairwise testing uses combinatorial techniques to ensure that each parameter value pair gets tested once against each parameter value pair of each other parameter, i.e., all pairs of parameter value pairs for any two different parameters get tested, while avoiding testing all combinations of parameter value pairs. If the test analyst uses a manual approach, a table is constructed with test cases represented by rows and one column for each parameter. The test analyst then populates the table with values such that all pairs of values can be identified in the table. See Black 09. Any entries in the table which are left blank can be filled with values by the test analyst using their own domain knowledge. There are a number of tools available to aid a test analyst in this task. See www.pairwise.org for samples. They require, as input, a list of the parameters and their values, and generate a suitable set of combinations of values from each parameter that covers all pairs of parameter value pairs. The output of the tool can be used as input for test cases. Note that the test analyst must supply the expected results for each combination that is created by the tools. Classification trees, see section 3.2.5, are often used in conjunction with pairwise testing, Bath 14. Classification tree design is supported by tools and enables combinations of parameters and their values to be visualized. Some tools offer a pairwise enhancement. This helps to identify the following information. Inputs to be used by the pairwise test technique. Particular combinations of interest, e.g., frequently used or a common source of defects. Particular combinations which are incompatible. This does not assume that the combined factors won't affect each other. They very well might, but should affect each other in acceptable ways. Logical relationships between variables. For example, if variable 1 equals x, then variable 2 cannot be y. Classification trees which capture these relationships are called feature models. Applicability. The problem of having too many combinations of parameter values manifests itself in at least two different situations related to testing. Some test items involve several parameters, each with a number.
Certified Tester, Advanced Level, Test Analyst, CTAL TA. Values make up the input data for the test cases. Furthermore, some systems may be configurable in a number of dimensions, resulting in a potentially large configuration space. In both these situations, pairwise testing can be used to identify a subset of combinations that is manageable and feasible. For parameters with many values, equivalence partitioning or some other selection mechanism may first be applied to each parameter individually to reduce the number of values for each parameter, before pairwise testing is applied to reduce the set of resulting combinations. Capturing the parameters and their respective values in a classification tree supports this activity.
These techniques are usually applied to the component integration, system, and system integration test levels. Limitations/difficulties. The major limitation with these techniques is the assumption that the results of a few tests are representative of all tests and that those few tests represent expected usage. If there is an unexpected interaction between certain variables, it may go undetected with this test technique if that particular combination is not tested. These techniques can be difficult to explain to a non-technical audience as they may not understand the logical reduction of tests. Any such explanation should be balanced by mentioning the results from empirical studies Kuhn 16, which showed that in the area of medical devices under study, 66% of failures were triggered by a single variable and 97% by either one variable or two variables interacting. There is a residual risk that pairwise testing may not detect systems failures where three or more variables interact. Identifying the parameters and their respective values is sometimes difficult to achieve. Therefore, this task should be performed with the support of classification trees where possible. See section 3.2.5. Finding a minimal set of combinations to satisfy a certain level of coverage is difficult to do manually. Tools may be used to find the smallest possible set of combinations. Some tools support the ability to force some combinations to be included in or excluded from the final selection of combinations. A test analyst may use this capability to emphasize or de-emphasize factors based on domain knowledge or product usage information. Coverage. The 100% pairwise coverage requires every pair of values of any pair of parameters be included in at least one combination. Types of defects. The most common type of defects found with this test technique is defects related to the combined values of two parameters. 3.2.7. Use case testing. Use case testing provides transactional, behavior-based tests that should emulate intended use of the component or system specified by the use case. Use cases are defined in terms of interactions between the actors and a component or system that accomplishes some goal. Actors can be human users, external hardware, or other components or systems. A common standard for use cases is provided in OMG-UML. Applicability. Use case testing is usually applied in system and acceptance testing. It may also be used in integration testing if the behavior of the components or systems is specified by use cases. Use cases are also often Certified Tester Advanced Level Test Analyst, CTAL, TA. Described in the use cases may be assigned to virtual users to create a realistic load on the system, so long as load and performance requirements are specified in them or for them. Limitations/difficulties. In order to be valid, the use cases must convey realistic user transactions. Use case specifications are a form of system design. The requirements of what users need to accomplish should come from users or user representatives and should be checked against organizational requirements before designing corresponding use cases. The value of a use case is reduced if it does not reflect real user and organizational requirements, or hinders rather than assists completion of user tasks. An accurate definition of the exception, alternative, and error handling behaviors is important for the coverage to be thorough. Use cases should be taken as a guideline but not a complete definition of what should be tested, as they may not provide a clear definition of the entire set of requirements. It may also be beneficial to create other models, such as flowcharts and/or decision tables, from the use case narrative to improve the accuracy of the testing and to verify the use case itself. As with other forms of specification, this is likely to reveal logical anomalies in the use case specification, if they exist. Coverage. The minimum acceptable level of coverage of a use case is to have one test case for the basic behavior and sufficient additional test cases to cover each alternative and error handling behavior. If a minimal test suite is required, multiple alternative behaviors may be incorporated into a test case provided they are mutually compatible. If better diagnostic capability is required, e.g., to assist in isolating defects, one additional test case per alternative behavior may be designed, although nested alternative behaviors will still require some of those behaviors to be amalgamated into a single test case, e.g., termination versus non-termination alternative behaviors within a retry exception behavior. Types of defects. Defects include mishandling of defined behaviors, missed alternative behaviors, incorrect processing of the conditions presented, and poorly implemented or incorrect error messages. 3.2.8 Combining techniques. Sometimes techniques are combined to create test cases. For example, the conditions identified in a decision table might be subjected to equivalence partitioning to discover multiple ways in which a condition might be satisfied. Test cases would then cover not only every combination of conditions, but also, for those conditions which are partitioned, additional test cases should be generated to cover the equivalence partitions. When selecting the particular technique to be applied, the test analyst should consider the applicability of the technique, the limitations and difficulties, and the goals of the testing in terms of coverage and defects to be detected. These aspects are described for the individual techniques covered in this chapter. There may not be a single best technique for a situation. Combining the suitable techniques will often be the most effective way to achieve the test objective set, assuming there is sufficient time and skill to correctly apply the techniques. 3.3 Experience-based test techniques. Experience-based testing utilizes the skill and intuition of the testers, along with their experience with similar applications or technologies, to target testing in order to increase defect detection. These test techniques range from quick tests, in which the tester has no formally pre-planned activities to perform, through pre-planned test sessions using test charters, to scripted testing sessions. They are almost always useful, but have particular value when aspects included in the following list of advantages can be achieved.
Certified Test Analyst Advanced Level Test Analyst, CTAL. It may be a good alternative to more structured approaches in cases where system documentation is lacking. It can be applied when testing time is severely restricted. It enables available expertise in the domain and technology to be applied in testing. This may include those not involved in testing, e.g., from business analysts, customers, or clients. It can provide early feedback to the developers. It helps the team become familiar with the software as it is produced. It is effective when operational failures are analyzed. It enables a diversity of test techniques to be applied. Experience-based testing has the following disadvantages. It may be inappropriate in systems requiring detailed test documentation. High levels of repeatability are difficult to achieve. The ability to precisely assess coverage is limited. Tests are less suited for subsequent automation. When using reactive and heuristic approaches, testers normally use experience-based testing, which is more reactive to events than pre-planned test approaches. In addition, execution and evaluation are concurrent tasks. Some structured approaches to experience-based testing are not entirely dynamic, i.e., the tests are not created entirely at the same time as the tester executes the test. This might be the case, for example, where error guessing is used to target particular aspects of the test object before test execution. Note that although some ideas on coverage are presented for the techniques discussed here, experience-based test techniques do not have formal coverage criteria. 3.31 Error guessing. When using the error guessing technique, a test analyst uses experience to guess the potential errors that might have been made when the code was being designed and developed. When the expected errors have been identified, a test analyst then determines the best methods to use to uncover the resulting defects. For example, if a test analyst expects the software will exhibit failures when an invalid password is entered, tests will be run to enter a variety of different values in the password field to verify if the error was indeed made and has resulted in a defect that can be seen as a failure when the tests are run. In addition to being used as a test technique,
Error guessing is also useful during risk analysis to identify potential failure modes. Myers 11. Applicability. Error guessing is done primarily during integration and system testing, but can be used at any test level. This technique is often used with other techniques and helps to broaden the scope of the existing test cases. Error guessing can also be used effectively when testing a new release of the software to test for common defects before starting more rigorous and scripted testing. Limitations, difficulties. The following limitations and difficulties apply to error guessing. Coverage is difficult to assess and varies widely with the capability and experience of the test analyst. It is best used by an experienced tester who is familiar with the types of defects that are commonly introduced in the type of code being tested.
Certified Tester, Advanced Level, Test Analyst, CTAL. It is commonly used but is frequently not documented and so may be less reproducible than other forms of testing. Test cases may be documented, but in a way that only the author understands and can reproduce. Coverage. When a defect taxonomy is used, coverage is determined by taking the number of taxonomy items tested divided by the total number of taxonomy items and stating coverage as a percentage. Without a defect taxonomy, coverage is limited by the experience and knowledge of the tester and the time available. The quantity of defects found from this technique will vary based on how well the tester can target problematic areas. Types of defects. Typical defects are usually those defined in the particular defect taxonomy or guessed by the test analyst that might not have been found in black box testing. 3.3.2 Checklist-based testing. When applying the checklist-based test technique, an experienced test analyst uses a high-level, generalized list of items to be noted, checked, or remembered, or a set of rules or criteria against which a test object has to be verified. These checklists are built based on a set of standards, experience, and other considerations. For example, a user interface standard checklist can be employed as the basis for testing an application. In Agile software development, checklists can be built from the acceptance criteria for a user story. Applicability. Checklist-based testing is most effective in projects with an experienced test team that is familiar with the software under test or familiar with the area covered by the checklist. For example, to successfully apply a user interface checklist, the test analyst may be familiar with user interface testing but not the specific system under test. Because checklists are high-level and tend to lack the detailed steps commonly found in test cases and test procedures, the knowledge of the tester is used to fill in the gaps. By removing the detailed steps, checklists are low maintenance and can be applied to multiple similar releases. Checklists are well suited to projects where software is released and changed quickly. This helps to reduce both the preparation and maintenance time for test documentation. They can be used for any test level and are also used for regression testing and smoke testing. Limitations/difficulties. The high-level nature of the checklists can affect the reproducibility of test results. It is possible that several testers will interpret the checklist differently and will follow different approaches to fulfill the checklist items. This may cause different test results, even though the same checklist is used. This can result in wider coverage, but reproducibility is sometimes sacrificed. Checklists may also result in overconfidence regarding the level of coverage that is achieved, since the actual testing depends on the tester's judgment. Checklists can be derived from more detailed test cases or lists and tend to grow over time. Maintenance is required to ensure that the checklists are covering the important aspects of the software under test. Coverage. Coverage can be determined by taking the number of checklist items tested divided by the total number of checklist items and stating coverage as a percentage. The coverage is as good as the checklist, but because of the high-level nature of the checklist, the results will vary based on the test analyst. Certified Tester Advanced Level, Test Analyst, CTALTA. Types of defects. Typical defects found with this technique cause failures resulting from varying the data, the sequence of steps, or the general workflow during testing. 3.3.3 Exploratory testing. Exploratory testing is characterized by the tester simultaneously learning about the test object and its defects, planning the testing work to be done, designing and executing the tests, and reporting the results. The tester dynamically adjusts test goals during execution and prepares only lightweight documentation. Whitaker 09. Applicability. Good exploratory testing is planned, interactive, and creative. It requires little documentation about the system to be tested, and is often used in situations where the documentation is not available or is not adequate for other test techniques. Exploratory testing is often used to add to other test techniques and to serve as a basis for the development of additional test cases. Exploratory testing is frequently used in agile software development to get user story testing done flexibly and quickly with only minimal documentation. However, the technique may also be applied to projects using a sequential development model. Limitations, difficulties. Exploratory testing does not provide any coverage measure. Moreover, reproducing the tests performed can be difficult. Using test charters to designate the areas to be covered in a test session and time boxing to determine the time allowed for the testing are techniques used to manage exploratory testing. At the end of a test session or set of test sessions, the test manager may hold a debriefing session to gather the test results and determine the test charters for the next test sessions. Another difficulty with exploratory testing sessions is to accurately track them in a test management system. This is sometimes done by creating test cases that are actually exploratory testing sessions. This allows the time allocated for the exploratory testing and the planned coverage to be tracked with the other test efforts. Since reproducibility may be difficult to achieve with exploratory testing, this can also cause problems when needing to recall the steps to reproduce a failure. Some organizations use the capture playback capability of a test automation tool to record the steps taken by an exploratory tester. This provides a complete record of all activities during the exploratory testing session or any experience-based testing session. Analyzing the details to find the actual cause of a failure can be tedious, but at least there is a record of all the steps that were involved. Other tools may be used to capture exploratory testing sessions, but these don't record the expected results because they don't capture the GUI interaction. In this case, the expected results must be noted down so that proper analysis of defects can be undertaken if needed. In general, it is recommended that notes also be taken while performing exploratory testing to support reproducibility where required. Coverage. Test charters may be designed for specific tasks, objectives, and deliverables. Exploratory testing sessions are then planned to achieve those criteria. The charter may also identify where to focus the test effort, what is in and out of scope of the test session, and what resources should be committed to complete the planned tests. A test session may be used to focus on particular defect types and other potentially problematic areas that can be addressed without the formality of scripted testing.
Certified Tester, Advanced Level, Test Analyst, CTAL. Types of defects. Typical defects found with exploratory testing are scenario-based issues that are missed during scripted functional suitability testing, issues that fall between functional boundaries, and workflow-related issues. Performance and security issues are also sometimes uncovered during exploratory testing. 3.3.4 Defect-Based Test Techniques. A defect-based test technique is one in which the type of defect sought is used as the basis for test design, with tests derived systematically from what is known about the type of defect. Unlike black box testing, which derives its tests from the test basis, defect-based testing derives tests from lists which focus on defects. In general, the lists may be organized into defect types, root causes, failure symptoms, and other defect-related data. Standard lists apply to multiple types of software and are not product-specific. Using these lists helps to leverage industry-standard knowledge to derive the particular tests. By adhering to industry-specific lists, metrics regarding defect occurrence can be tracked across projects and even across organizations.
The most common defect lists are those which are organization or project specific and make use of specific expertise and experience. Defect-based testing may also use lists of identified risks and risk scenarios as a basis for targeting testing. This test technique allows a test analyst to target a specific type of defect or to work systematically through a list of known and common defects of a particular type. From this information, the test analyst creates the test conditions and test cases that will cause the defect to manifest itself, if it exists. Applicability. Defect-based testing can be applied at any test level, but is most commonly applied during system testing. Limitations, difficulties. Multiple defect taxonomies exist and may be focused on particular types of testing, such as usability. It is important to pick a taxonomy that is applicable to the software under test, if any are available. For example, there may not be any taxonomies available for innovative software. Some organizations have compiled their own taxonomies of likely or frequently seen defects. Whatever defect taxonomy is used, it is important to define the expected coverage prior to starting the testing. Coverage. The technique provides coverage criteria which are used to determine when all the useful test cases have been identified. Coverage items may be structural elements, specification elements, usage scenarios, or any combination of these depending on the defect list. As a practical matter, the coverage criteria for defect-based test techniques tend to be less systematic than for black box test techniques, in that only general rules for coverage are given, and the specific decision about what constitutes the limit of useful coverage is discretionary. As with other techniques, the coverage criteria do not mean that the entire set of tests is complete, but rather that defects being considered no longer suggest any useful tests based on that technique. Types of defects. The types of defects discovered usually depend on the defect taxonomy in use. For example, if a user interface defect list is used, the majority of the discovered defects would likely be user interface related, but other defects can be discovered as a byproduct of the specific testing.
Certified Tester Advanced Level Test Analyst, CTAL. 3.4. Applying the most appropriate technique. Black box and experience-based test techniques are most effective when used together. Experience-based test techniques fill the gaps in achieving test objectives that result from any systematic weaknesses in black box test techniques. There is not one perfect technique for all situations. It is important for the test analyst to understand the advantages and disadvantages of each technique and to be able to select the best technique or set of techniques for the situation, considering the project type, schedule, access to information, skills of the tester, and other factors that can influence the selection. In the discussion of each black box and experience-based test technique, see sections 3.2 and 3.3 respectively, the information provided in applicability, limitation/difficulties, and coverage guides a test analyst in selecting the most appropriate test techniques to apply. Certified Tester Advanced Level Test Analyst, CTALTA. 4. Testing Software Quality Characteristics, 180 mins. Keywords: accessibility, compatibility, functional appropriateness, functional completeness, functional correctness, functional suitability, interoperability, learnability, operability, software usability measurement inventory, SUMI, usability, user error protection, user experience, user interface aesthetics, website analysis and measurement inventory, WAMMI. Learning objectives for testing software quality characteristics. 4.1. Introduction. No learning objectives. 4.2. Quality characteristics for business domain testing. TA 4.2.1. K2. Explain what test techniques are appropriate to test the functional completeness, functional correctness, and functional appropriateness. TA 4.2.2. K2. Define the typical defects to be targeted for the functional completeness, functional correctness, and functional appropriateness characteristics. TA 4.2.3, K2. Define when the functional completeness, correctness, and appropriateness characteristics should be tested in the software development lifecycle. TA 4.2.4, K2. Explain the approaches that would be suitable to verify and validate both the implementation of the usability requirements and the fulfillment of the user's expectations. TA 4.2.5, K2. Explain the role of the test analyst in interoperability testing, including identification of the defects to be targeted. TA 4.2.6, K2. Explain the role of the test analyst in portability testing, including identification of the defects to be targeted. TA 4.2.7, K4. For a given set of requirements, determine the test conditions required to verify the functional and/or non-functional quality characteristics within the scope of the test analyst.
Certified Tester Advanced Level Test Analyst, CTAL TA. 4.1 Introduction. While the previous chapter described specific techniques available to the tester, this chapter considers the application of those techniques in evaluating the characteristics used to describe the quality of software applications or systems. This syllabus discusses the quality characteristics which may be evaluated by a test analyst. The attributes to be evaluated by the technical test analyst are considered in the Advanced Technical Test Analyst Syllabus, CTAL-TTA. The description of product quality characteristics provided in ISO 2501 is used as a guide to describe the characteristics. The ISO software quality model divides product quality into different product quality characteristics, each of which may have subcharacteristics. These are shown in the table below, together with an indication of which subcharacteristics are covered by the Test Analyst and Technical Test Analyst syllabi. Characteristic, subcharacteristics, test, analyst, technical, test, analyst, functional suitability, functional correctness, functional appropriateness, functional completeness, X, reliability, maturity, fault tolerance, recoverability, availability, X, usability, appropriateness, recognizability, learnability, operability, user interface aesthetics, user error protection, accessibility, X, performance efficiency, time behavior, resource utilization, capacity, X, maintainability, analyzability, modifiability, testability, modularity, reusability, X, portability, adaptability, installability, replaceability, X, security, confidentiality, integrity, non-repudiation, accountability, authenticity, X, compatibility, coexistence, X, interoperability, X. While this allocation of work may vary in different organizations, it is the one that is followed in the associated ISTQB syllabi. For all of the quality characteristics and subcharacteristics discussed in this section, the typical risks must be recognized so that an appropriate test strategy can be formed and documented. Quality characteristic testing requires particular attention to SDLC timing, required tools, software and documentation availability, and technical expertise. Without a strategy to deal with each characteristic and its unique testing needs, the tester may not have adequate planning, ramp-up, and test execution time built into the schedule. Bath 14. Some of this testing, e.g. usability testing, can require allocation of special human resources, extensive planning, dedicated labs, specific tools, specialized testing skills, and, in most cases, a significant amount of time. In some cases, usability testing may be performed by a separate group of usability or user experience experts. While the test analyst may not be responsible for the quality characteristics that require a more technical approach, it is important that the test analyst is aware of the other characteristics and understands the overlapping areas for testing. For example, a test object that fails performance testing may likely fail in
Certified Tester Advanced Level Test Analyst CTAL TA. Issues with some components is probably not ready for portability testing, as that will tend to obscure the more basic problems when the environment is changed. 4.2 Quality Characteristics for Business Domain Testing. Functional suitability testing is a primary focus for the test analyst. Functional suitability testing is focused on what the test object does. The test basis for functional suitability testing is generally requirements, a specification, specific domain expertise, or implied need. Functional suitability tests vary according to the test level in which they are conducted and can also be influenced by the SDLC. For example, a functional suitability test conducted during integration testing will test the functional suitability of interfacing components which implement a single defined function. At the system test level, functional suitability tests include testing the functional suitability of the system as a whole. For systems of systems, functional suitability testing will focus primarily on end-to-end testing across the integrated systems. A wide variety of test techniques are employed during functional suitability testing. See Chapter 3. In Agile software development, functional suitability testing usually includes the following: testing the specific functionality, e.g. user stories, planned for implementation in the particular iteration. Regression testing for all unchanged functionality. In addition to the functional suitability testing covered in this section, there are also certain quality characteristics that are part of the test analyst's area of responsibility that are considered to be non-functional, focused on how the test object delivers the functionality, testing areas. 4.2.1 Functional Correctness Testing. Functional correctness involves verifying the application's adherence to the specified or implied requirements, and may also include computational accuracy. Functional correctness testing employs many of the test techniques explained in Chapter 3, and often uses the specification or a legacy system as the test oracle. Functional correctness testing can be conducted at any test level and is targeted on incorrect handling of data or situations. 4.2.2 Functional Appropriateness Testing. Functional appropriateness testing involves evaluating and validating the appropriateness of a set of functions for its intended specified tasks. This testing can be based on the functional design, e.g. use cases and/or user stories. Functional appropriateness testing is usually conducted during system testing, but may also be conducted during the later stages of integration testing. Defects discovered in this testing are indications that the system will not be able to meet the needs of the user in a way that will be considered acceptable. 4.2.3 Functional Completeness Testing. Functional completeness testing is performed to determine the coverage of specified tasks and user objectives by the implemented functionality. Traceability between specification items, e.g. requirements, user stories, use cases, and the implemented functionality, e.g. function, component, workflow, is essential to enable required functional completeness to be determined. Measuring functional completeness may vary according to the particular test level and/or the SDLC used. For example, functional completeness for Agile software development may be based on implemented user stories and features. Functional completeness for systems integration testing may focus on the coverage of high-level business processes.
Certified Tester Advanced Level, Test Analyst. Determining functional completeness is generally supported by test management tools if the test analyst is maintaining the traceability between the test cases and the functional specification items. Lower than expected levels of functional completeness are indications that the system has not been fully implemented. 4.2.4 Interoperability Testing. Interoperability testing verifies the exchange of information between two or more systems or components. Tests focus on the ability to exchange information and subsequently use the information that has been exchanged. Testing should cover all the intended target environments, including variations in the hardware, software, middleware, operating system, etc., to ensure the data exchange will work properly.
In reality, this may only be feasible for a relatively small number of environments. In that case, interoperability testing may be limited to a selected representative group of environments. Specifying tests for interoperability requires that combinations of the intended target environments are identified, configured, and available to the test team. These environments are then tested using a selection of functional suitability test cases which exercise the various data exchange points present in the environment. Interoperability relates to how different components and software systems interact with each other. Software with good interoperability characteristics can be integrated with a number of other systems without requiring major changes or significant impact on non-functional behavior. The number of changes and the effort required to implement and test those changes may be used as a measure of interoperability. Testing for software interoperability may, for example, focus on the following design features: use of industry-wide communication standards, such as XML, ability to automatically detect the communication needs of the systems it interacts with and adjust accordingly. Interoperability testing may be particularly significant for the following: commercial off-the-shelf software products and tools, applications based on a system of systems, systems based on the Internet of Things, web services with connectivity to other systems. This type of testing is performed during component integration and system integration testing. At the system integration level, this type of testing is conducted to determine how well the fully developed system interacts with other systems. Because systems may interoperate on multiple levels, the test analyst must understand these interactions and be able to create the conditions that will exercise the various interactions. For example, if two systems will exchange data, the test analyst must be able to create the necessary data and the transactions required to perform the data exchange. It is important to remember that all interactions may not be clearly specified in the requirements documents. Instead, many of these interactions will be defined only in the system architecture and design documents. The test analyst must be able and prepared to examine these documents to determine the points of information exchange between systems and between the system and its environment to ensure all are tested. Techniques such as equivalence partitioning, boundary value analysis, decision tables, state transition diagrams, use cases, and pairwise testing are all applicable to interoperability testing. Typical defects found include incorrect data exchange between interacting components. 4.2.5 Usability Evaluation. Test analysts are often in the position to coordinate and support the evaluation of usability. This may be Certified Tester Advanced Level Test Analyst, CTAL. Do this effectively, a test analyst must understand the principal aspects, goals, and approaches involved in these types of testing. Please refer to the ISTQB Specialist Syllabus in Usability Testing, ISTQB UT-SYL, for details beyond the description provided in this section. It is important to understand why users might have difficulty using the system or do not have a positive user experience, UX, e.g., with using software for entertainment. To gain this understanding, it is first necessary to appreciate that the term user may apply to a wide range of different types of personas, ranging from IT experts to children to people with disabilities. 4.2.5.1 Usability Aspects. The following are the three aspects considered in this section. Bullet, usability in the sense according to the ISO 2510 standard. Bullet, user experience, UX, as a generalization of usability. Bullet, accessibility as a sub-characteristic of usability. Usability. Usability testing targets software defects that impact a user's ability to perform tasks via the user interface. Such defects may affect the user's ability to achieve their goals effectively or efficiently, or with satisfaction. Usability problems can lead to confusion, error, delay, or outright failure to complete some task on the part of the user. The following are the sub-characteristics of usability, ISO 2500. For their definitions, see ISTQB glossary. Bullet, appropriateness recognizability, that is, understandability. Bullet, learnability. Bullet, operatability. Bullet, user interface aesthetics, that is, attractiveness. Bullet, user error protection. Bullet, accessibility, see below. User experience. User experience evaluation addresses the whole user experience with the test object, not just the direct interaction. This is of particular importance for test objects where factors such as enjoyment and user satisfaction are critical for business success. Typical factors which influence user experience include the following. Bullet, brand image, that is, the user's trust in the manufacturer. Bullet, interactive behavior. Bullet, the helpfulness of the test object, including help system, support, and training. Accessibility. It is important to consider the accessibility to software for those with particular needs or restrictions for its use. This includes those with disabilities. Accessibility testing should consider the relevant standards such as the Web Content Accessibility Guidelines, WCAG, and legislation, such as the Disability Discrimination Acts, Northern Ireland, Australia, Equality Act 2010, England, Scotland, Wales, and Section 508, US. Accessibility, similar to usability, must be considered when conducting design activities. Testing often occurs during the integration levels and continues through system testing and into the acceptance testing levels. Defects are usually determined when the software fails to meet the designated regulations or standards defined for the software. Typical measures to improve accessibility focus on the opportunities provided for users with disabilities to interact with the application. These include the following: voice recognition for inputs. Certified Tester, Advanced Level, Test Analyst, CTAL. Enabling text to be resized without loss of content or functionality. Accessibility guidelines support the test analyst by providing a source of information and checklists which can be used for testing. Examples of accessibility guidelines are given in ISTQB_UT_SYL. In addition, tools and browser plugins are available to help testers identify accessibility issues, such as poor color choice in web pages that violate guidelines for colorblindness. 4.2.5.2 Usability Evaluation Approaches. Usability, user experience, and accessibility may be tested by one or more of the following approaches. Usability testing. Usability reviews. User surveys and questionnaires. Usability testing. Usability testing evaluates the ease by which users can use or learn to use the system to reach a specified goal in a specific context. Usability testing is directed at measuring the following: effectivity, capability of the test object to enable users to achieve specified goals with accuracy and completeness in a specified context of use. Efficiency, capability of the test object to enable users to expend appropriate amounts of resources in relation to the effectiveness achieved in a specified context of use. Satisfaction, capability of the test object to satisfy users in a specified context of use. It is important to note that designing and specifying usability tests is often conducted by the test analyst, in cooperation with testers who have special usability testing skills and usability design engineers who understand the human-centered design process. See ISTQB_UT_SYL. Usability reviews. Inspections and reviews are a type of testing conducted from a usability perspective which help to increase the user's level of involvement. This can be cost-effective by finding usability problems in requirements, specifications, and designs early in the SDLC. Heuristic evaluation, systematic inspection of a user interface design for usability, can be used to find the usability problems in the design so that they can be addressed as part of an iterative design process. This involves having a small set of evaluators examine the interface and judge its compliance with recognized usability principles, the heuristics. Reviews are more effective when the user interface is more visible. For example, Sample screenshots are usually easier to understand and interpret than just describing the functionality given by a particular screen. Visualization is important for an adequate usability review of the documentation. User surveys and questionnaires. Survey and questionnaire techniques may be applied to gather observations and feedback regarding user behavior with the system. Standardized and publicly available surveys such as Software Usability Measurement Inventory, SUMI, and Website Analysis and Measurement Inventory, WAMI, permit benchmarking against a database of previous usability measurements. In addition, since SUMI provides tangible measurements of usability, this can provide a set of completion/acceptance criteria. 4.2.6 Portability Testing. Portability tests relate to the degree to which a software component or system can be transferred into its intended environment, either as a new installation or from an existing environment. The ISO 25010 classification of product quality characteristics includes the following subcharacteristics of portability. Installability. Certified Tester Advanced Level Test Analyst, CTAL TA. Replaceability. The task of identifying risks and designing tests for portability characteristics is shared between the test analyst and the technical test analyst. See ISTQB Alt LTA SYL Section 4.7. 4.2.6.1 Installability Testing. Installability testing is conducted on the software, and written procedures are used to install and deinstall the software on its target environment. The typical testing objectives that are the focus of the test analyst include validating that different configurations of the software can be successfully installed. Where a large number of parameters may be configured, the test analyst may design tests using the pairwise technique to reduce the number of parameter combinations tested and focus on particular configurations of interest, e.g., those frequently used. Testing the functional correctness of installation and deinstallation procedures. Performing functional suitability tests following an installation or deinstallation to detect any defects which may have been introduced, e.g., incorrect configurations, functions not available. Identifying usability issues in installation and deinstallation procedures, e.g., to validate that users are provided with understandable instructions and feedback/error messages when executing the procedure. 4.2.6.2 Adaptability Testing. Adaptability testing checks whether a given application can be adapted effectively and efficiently to function correctly in all intended target environments: hardware, software, middleware, operating system, cloud, etc. The test analyst supports adaptability testing by identifying the intended target environments, e.g., versions of different mobile operating systems supported, different versions of browsers which may be used, and designing tests that cover combinations of these environments. The target environments are then tested using a selection of functional suitability test cases, which exercise the various components present in the environment. 4.2.6.3 Replaceability Testing. Replaceability testing focuses on the ability of software components or versions within a system to be exchanged for others. This may be particularly relevant for system architectures based on the Internet of Things, where the exchange of different hardware devices and/or software installations is a common occurrence. For example, a hardware device used in a warehouse to register and control stock levels may be replaced by a more advanced hardware device, e.g., with a better scanner. Or the installed software may be upgraded with a new version that enables stock replacement orders to be automatically issued to a supplier system. Replaceability tests may be performed by the test analyst in parallel with functional integration tests where more than one alternative component is available for integration into the complete system.
Certified Tester, Advanced Level, Test Analyst, CTAL. 5. Reviews, 120 mens. Keywords, checklist-based reviewing. Learning objectives for reviews. 5.1 Introduction. No learning objectives. 5.2. Using checklists in reviews. TA-5.2.1, K3. Identify problems in a requirement specification according to checklist information provided in the syllabus. TA-5.2.2, K3. Identify problems in a user story according to checklist information provided in the syllabus.
Certified Tester Advanced Level Test Analyst, CTAL-TA. 5.1 Introduction. Test analysts must be active participants in the review process, providing their unique views. When done properly, reviews can be the single biggest and most cost-effective contributor to overall delivered quality. 5.2 Using checklists in reviews. Checklist-based reviewing is the most common technique used by a test analyst when reviewing the test basis. Checklists are used during reviews to remind the participants to check specific points during the review. They can also help to depersonalize the review, e.g., this is the same checklist we use for every review. We are not targeting only your work product. Checklist-based reviewing can be performed generically for all reviews or can focus on specific quality characteristics, areas, or types of documents. For example, a generic checklist might verify the general document properties such as having a unique identifier, no references marked to be determined, proper formatting, and similar conformance items. A specific checklist for a requirements document might contain checks for the proper use of the terms shall and should, checks for the testability of each stated requirement, and so forth. The format of the requirements may also indicate the type of checklist to be used. A requirements document that is in narrative text format will have different review criteria than one that is based on diagrams. Checklists may also be oriented toward a particular aspect, such as a programmer/architect skill set or a tester skill set. In the case of the test analyst, the tester skill set checklist would be the most appropriate. A certain risk level, e.g. in safety-critical systems. The checklists will typically include the specific information needed for the risk level. A specific test technique. The checklist will focus on the information needed for a particular technique, e.g. rules to be represented in a decision table. A particular specification item, such as a requirement, use case, or user story. These are discussed in the following sections and generally have a different focus than those used by a technical test analyst for the review of code or architecture. 5.2.1 Requirements Reviews. The following items are an example of what a requirements-oriented checklist could include. Source of the requirement, e.g., person, department. Testability of each requirement. Priority of each requirement. Acceptance criteria for each requirement. Availability of a use case calling structure, if applicable. Unique identification of each requirement, use case, user story. Versioning of each requirement. Use case, user story. Traceability for each requirement from business/marketing requirements. Traceability between requirements and/or use cases, if applicable. Use of consistent terminology, e.g., uses a glossary. It is important to remember that if a requirement is not testable, meaning that it is defined in such a way that the test analyst cannot determine how to test it, then there is a defect in that requirement. For Certified Tester Advanced Level Test Analyst, CTAL. The test analysts determine if the software is user-friendly or even very user-friendly. If, instead, the requirement says the software must conform to the usability standards stated in the usability standards document, version XXX, and if the usability standards document exists, then this is a testable requirement. It is also an overarching requirement because this one requirement applies to every item in the interface. In this case, this one requirement could easily spawn many individual test cases in a non-trivial application. Traceability from this requirement, or perhaps from the usability standards document, to the test cases is also critical, because if the referenced usability specifications should change, all the test cases will need to be reviewed and updated as needed. A requirement is also untestable if the tester is unable to determine whether the test passed or failed, or is unable to construct a test that can pass or fail. For example, system shall be available 100% of the time, 24 hours per day, 7 days per week, 365 or 366 days a year is untestable. A simple checklist, 1, for use case reviews may include the following questions. Is the basic behavior, path, clearly defined? Are all alternative behaviors, paths, identified, complete with error handling? Are the user interface messages defined? Is there only one basic behavior? There should be. Otherwise, there are multiple use cases. Is each behavior testable? 5.2.2 User Story Reviews. In Agile software development, requirements usually take the form of user stories. These stories represent small units of demonstrable functionality. Whereas a use case is a user transaction that traverses multiple areas of functionality, a user story is a more isolated feature and is generally scoped by the time it takes to develop it. A checklist, 1, for a user story could include the following. Is the story appropriate for the target iteration, sprint? Is the story written from the view of the person who is requesting it? Are the acceptance criteria defined and testable? Is the feature clearly defined and distinct? Is the story independent of any others? Is the story prioritized? Does the story follow the commonly used format? As a type of user, I want some goal so that some reason. CHON 40. If the story defines a new interface, then using a generic story checklist, such as the one above, and a detailed user interface checklist would be appropriate. 5.2.3 Tailoring Checklists. A checklist can be tailored based on the following. Organization, e.g., considering company policies, standards, conventions, legal constraints. Project development effort, e.g., focus, technical standards, risks. The type of work product being reviewed, e.g., code reviews might be tailored to specific programming languages. The risk level of the work product being reviewed. Test techniques to be used. Good checklists will find problems and will also help to start discussions regarding other items that might not have been specifically referenced in the checklist. Using a combination of checklists is a strong way. Certified Tester Advanced Level Test Analyst, CTAL. To ensure a review achieves the highest quality work product. Using checklist-based reviewing with standard checklists, such as those referenced in the foundation-level syllabus, and developing organizationally specific checklists, such as the ones shown above, will help the test analyst be effective in reviews. For more information on reviews and inspections, see Gilb 93 and Uyghurs 30. Further examples of checklists can be obtained from the references in Section 7.4. Certified Tester Advanced Level Test Analyst, CTAL. 6. Test Tools and Automation, 90 mins. Keywords, keyword-driven testing, test data preparation, test design, test execution, test script. Learning objectives for test tools and automation. 6.1. Introduction. No learning objectives. 6.2. Keyword-driven testing. TA-6.2-1. K3. For a given scenario, determine the appropriate activities for a test analyst in a keyword-driven testing project. 6.3. Types of test tools. TA-6.3-1. K2. Explain the usage and types of test tools applied in test design, test data preparation, and test execution. Certified Tester Advanced Level Test Analyst, CTAL. 6.1 Introduction. Test tools can greatly improve the efficiency and accuracy of testing. The test tools and automation approaches which are used by a test analyst are described in this chapter. It should be noted that test analysts work together with developers, test automation engineers, and technical test analysts to create test automation solutions. Keyword-driven testing, in particular, involves the test analyst and leverages their experience with the business and the system functionality. Further information on the subject of test automation and the role of the test automation engineer is provided in the ISTQB Advanced Level Test Automation Engineer Syllabus, ISTQB TAE SIL. 6.2 Keyword-Driven Testing. Keyword-driven testing is one of the principal test automation approaches and involves the test analyst in providing the main inputs, keywords, and data. Keywords, sometimes referred to as action words, are mostly, but not exclusively, used to represent high-level business interactions with a system, e.g., cancel order. Each keyword is typically used to represent a number of detailed interactions between an actor and the system under test. Sequences of keywords, including relevant test data, are used to specify test cases. Buwalda 02. In test automation, a keyword is implemented as one or more executable test scripts. Tools read test cases written as a sequence of keywords that call the appropriate test scripts which implement the keyword functionality. The scripts are implemented in a highly modular manner to enable easy mapping to specific keywords. Programming skills are needed to implement these modular scripts. The following are the primary advantages of keyword-driven testing. Keywords that relate to a particular application or business domain can be defined by domain experts. This can make the task of test case specification more efficient. A person with primarily domain expertise can benefit from automatic test case execution once the keywords have been implemented as scripts without having to understand the underlying automation code. Using a modular writing technique enables efficient maintenance of test cases by the test automation engineer when changes to the functionality and to the interface to the software under test. Bath 14. Test case specifications are independent of their implementation. Test analysts usually create and maintain the keyword action word data. They must realize that the task of script development is still necessary for implementing the keywords. Once the keywords and data to be used have been defined, the test automator, e.g., technical test analyst or test automation engineer, translates the business process keywords and lower-level actions into automated test scripts. While keyword-driven testing is usually run during system testing, code development may start as early as the test design. In an iterative environment, particularly when continuous integration, continuous deployment are used, test automation development is a continuous process. Once the input keywords and data are created, the test analyst assumes responsibility to execute the test scripts containing the keywords and to analyze any failures that may occur. When an anomaly is detected, the test analyst should assist in investigating the cause of failure to determine if the defect is with the keywords, the input data, the test automation script itself, or with the Certified Test Analyst level. Test Analyst, CTAL. Same data manually to see if the failure is in the application itself. If this does not show a failure, the test analyst should review the sequence of tests that led up to the failure to determine if the problem occurred in a previous step, perhaps by introducing incorrect input data, but the defect did not surface until later in the processing. If the test analyst is unable to determine the cause of failure, the troubleshooting information should be passed to the technical test analyst or developer for further analysis. 6.3 Types of test tools. Much of a test analyst's job requires the effective use of tools. This effectiveness is enhanced by the following: knowing which tools to use, knowing that tools can increase the efficiency of the test effort, e.g., by helping to provide better coverage in the time allowed. 6.3.1 Test design tools. Test design tools are used to help create test cases and test data to be applied for testing. These tools may work from specific requirements document formats, models, e.g. UML, or inputs provided by the test analyst. Test design tools are often designed and built to work with particular formats and particular tools, such as specific requirements management tools. Test design tools can provide information for the test analyst to use when determining the types of tests that are needed to obtain the particular targeted level of coverage, confidence in the system, or product risk mitigation actions. For example, classification tree tools generate and display the set of combinations that is needed to reach full coverage based on a selected coverage criterion. This information then can be used by the test analyst to determine the test cases that must be executed. 6.3.2 Test Data Preparation Tools. Test data preparation tools can provide the following benefits. Analyze a document, such as a requirements document or even the source code, to determine the data required during testing to achieve a level of coverage. Take a data set from a production system and scrub or anonymize it to remove any personal information while still maintaining the internal integrity of that data. The scrubbed data can then be used for testing without the risk of a security leak or misuse of personal information. This is particularly important where large volumes of realistic data are required and where security and data privacy risks apply. Generate synthetic test data from given sets of input parameters, e.g., for use in random testing. Some of these tools will analyze the database structure to determine what inputs will be required from the test analyst. 6.3.3 Automated Test Execution Tools. Test execution tools are used by test analysts at all test levels to run automated tests and check the actual results. The objective of using a test execution tool is typically one or more of the following: to reduce costs in terms of effort and/or time, to run more tests, to run the same test in many environments, to make test execution more repeatable, to run tests that would be impossible to run manually, i.e., large data validation tests. These objectives often overlap into the main objectives of increasing coverage while reducing costs. Certified Tester, Advanced Level, Test Analyst, CTALTA. The return on investment for test execution tools is usually highest when automating regression tests because of the low level of maintenance expected and the repeated execution of the tests. Automating smoke tests can also be an effective use of automation due to the frequent use of the tests, the need for a quick test result, and, although the maintenance cost may be higher, the ability to have an automated way to evaluate a new build in a continuous integration environment. Test execution tools are commonly used during system and integration testing. Some tools, particularly API test tools, may also be used in component testing. Leveraging the tools where they are most applicable will help to improve the return on investment. Certified Tester Advanced Level Test Analyst. 7. References. 7.1 Standards. ISO 25050. ISO/IEC 25010-2011, Systems and Software Engineering, Systems and Software, Quality Requirements and Evaluation. SQUAR, System and Software Quality Models, Chapter 4. ISO 29001-19. ISO/IEC/IEEE 29001-19-4, Software and Systems Engineering, Software Testing, Part 4, Test Techniques, 2015. OMG DMN. Object Management Group, OMG Decision Model and Notation, TM. Version 1.3, December 2019, URL www.omg.org/spec/DMN, Chapter 8. OMG UML. Object Management Group, OMG Unified Modeling Language, version 2.5.1, December 2017, URL www.omg.spec/uml. RTCA DO-178C/ED12C. Software considerations in airborne systems and equipment. Certification RTCA EuroK ED12C 2013, Chapter 1. 7.2 ISTQB and IREB documents. IREB CPRE IRB Certified Professional for Requirements Engineering Foundation Level. Syllabus version 2.2.2 2017. ISTQB AL Overview. ISTQB Advanced Level Overview version 2.0. ISTQB AL TTA Cell. ISTQB Advanced Level Technical Test Analyst Syllabus version 2019. ISTQB FL Cell. ISTQB Foundation Level Syllabus version 2018. ISTQB Glossary. Standard glossary of terms used in software testing. URL https://glossary.istqb.org. ISTQB AL TASIL. ISTQB Advanced Level Test Automation Engineer Syllabus version 2017. ISTQB UTSIL. ISTQB Foundation Level Specialist Syllabus Usability Testing version 2018. 7.3 Books and Articles. GBAT 14, Graham Bath, Judy McKay, The Software Test Engineer's Handbook, 2nd edition, Rocky Nook, 2014, ISBN 978-1933-522-4. Certified Tester Advanced Level Test Analyst CTAL TA. Black 02. Rex Black, Managing the Testing Process, 2nd edition, John Wiley & Sons, New York, 2002, ISBN 0-471-22398-0. Black 07. Rex Black, Pragmatic Software Testing, Becoming an Effective and Efficient Test Professional, John Wiley & Sons, 2007, ISBN 978-0-470-12790-2. Black 09. Rex Black, Advanced Software Testing, Volume 1, Rocky Nook, 2009, ISBN 978-1-393-522-19. Buwalda 02. Hans Buwalda, Integrated Test Design and Automation, Using the Test Frame Method, Addison Wesley Longman, 2002, ISBN 0-201-73725-6. Chow 1978. T.S. Chow, Testing Software Design Modeled by Finite State Machines, IEEE Transactions on Software Engineering, Volume SE4, Issue 3, May 1978, pp. 178-187. Cone 04. Mite Cone, User Stories Applied for Agile Software Development, Addison Wesley Professional, 2004, ISBN 0-321-20568-5. Copeland 04. Lee Copeland, A Practitioner's Guide to Software Test Design, Artec House, 2004, ISBN 1-580-3719-X. Craig 02. Rick David Craig, Stephen P. Jaskiel, Systematic Software Testing, Artec House, 2002, ISBN 1-580-535-08-9. Forgács 19. István Forgács, Attila Kovács, Practical Test Design, BCS, 2019, ISBN
0-1-780-174-723. Gill 93. Tom Gill, Dorothy Graham, Software Inspection, Addison Wesley, 1993. ISBN 0-201-631-81-4. Koeman 06. Tim Koeman, Leo von der Alst, Bart Broekman, Mickey Vroon, TMAP Next for result-driven testing. UTN Publishers, 2006. ISBN 90-721-948-02. Kuhn 16. Richard Kuhn et al. Introduction to Combinatorial Testing. CRC Press, 2016. ISBN 978-0-429-18515-1. Mosley 93. Daniel J. Mosley, The Handbook of MIS Application Software Testing. Jordan Press, Prentice Hall, 1993. ISBN 978-0-13-9070-07-5. Myers 11. Glenford J. Myers, The Art of Software Testing. 3rd edition, John Wiley & Sons, 2011. ISBN 978-1-1103-916-4. Offutt 16. Jeff Offutt, Paul Amann, Introduction to Software Testing, 2nd edition, Cambridge University Press, 2016. ISBN 13-103-107-17201-2. Van Veenendaal 12. Eric Van Veenendaal, Practical Risk-Based Testing, Product Risk Management, The Prisma Method. UTN Publishers, 2012. ISBN 978-949-09-80670. Weigers 13. Carl Weigers, Software Requirements 2. Microsoft Press, 2003. ISBN 0-735-618-79-8. Whitcatter 13. James Whitcatter, How to Break Software. Addison Wesley, 2003. ISBN 0-201-79193.
Certified Tester Advanced Level Test Analyst. CTAL TA. James Whitaker, Exploratory Software Testing, Tips, Tricks, Tours, and Techniques to Guide Test Design. Addison Wesley, 2009. ISBN 0-321-63641. 7.4. Other references. The following references point to information available on the Internet and elsewhere. Even though these references were checked at the time of publication of this advanced level syllabus, the ISTQB cannot be held responsible if the references are not available anymore. Point. Chapter 3. Dash. Cherwonka, Jakic, www.pairwise.org. Dash. Defect Taxonomy, www.testingeducation.org/a/bsct2.pdf. Dash. Sample Defect Taxonomy based on Boris Beiser's work. init.uni2.dk/vinter/bugtax.doc. Dash. Good overview of various taxonomies. testingeducation.org/a/bugtax.pdf. Dash. Heuristic Risk-Based Testing by James Bach. Dash. Exploring Exploratory Testing, Sem Connor and Andy Tinkham. www.caner.com/pdfs/exploring exploratory testing.pdf. Dash. Petticord, Brett, an Exploratory Testing Workshop Report. www.testingcraft.com/exploratory petticord. Dash. Chapter 5. http://tap.net/checklists and templates.
Certified Tester, Advanced Level, Test Analyst, CTAL. 8. Appendix A. The following table is derived from the complete table provided in ISO 25010. It focuses only on the quality characteristics covered in the Test Analyst syllabus and compares the terms used in ISO 9126 as used in the 2012 version of the syllabus with those in the newer ISO 25010 as used in this version. ISO IEC 25010, ISO IEC 91261. Notes: functional suitability, functionality, functional completeness, functional correctness, accuracy, functional appropriateness, suitability, interoperability, move to compatibility, usability, appropriateness recognizability, understandability, new name, learnability, operability, user error protection, new subcharacteristic, user interface aesthetics, attractiveness, new name, accessibility, new subcharacteristic, compatibility, new definition, interoperability, coexistence, covered in Technical Test Analyst.
Certified Tester Advanced Level, Test Analyst, CTAL TA. 9. Index. Zero Switch, 29. Accessibility, 39. Accuracy Testing, 41. Action Words, 51. Activities, 11. Adaptability Testing, 45. Agile Software Development, 12, 13, 48. Anonymize, 52. Applying the Best Technique, 38. Black Box Test Technique, 23. Black Box Test Techniques, 24. Boundary Value Analysis, 23, 26. Breadth First, 22. Checklist-Based Reviewing, 47. Checklist-Based Testing, 23, 35. Checklists in Reviews, 47. Classification Tree, 23, 30, 31. Combinatorial Techniques, 25. Combining Techniques, 33. Compatibility, 39. Decision Table, 23, 27. Defect Taxonomy, 23. Defect-Based Test Technique, 23, 37. Depth First, 22. Equivalence Partitioning, 23, 24. Error Guessing, 23, 34. Exit Criteria, 10. Experience-Based Test Technique, 23. Experience-Based Test Techniques, 18, 33, 34, 38. Experience-Based Testing, 23. Exploratory Testing, 23, 36. Functional Appropriateness, 39. Functional Appropriateness Testing, 41. Functional Completeness, 39. Functional Completeness Testing, 41. Functional Correctness, 39. Functional Correctness Testing, 41. Functional Suitability, 39. Heuristic, 44. High-Level Test Case, 10, 13, 15. Installability, 45. Interoperability, 39. Interoperability Testing, 42. ISO 9126, 40. Keywords, 51. Learnability, 39. Low-Level Test Case, 10, 13, 14. NIT, 29. Operability, 39. Pairwise Testing, 23, 31, 32, 42. Portability Testing, 44. Product Risk, 13, 19. Quality Characteristics, 40. Quality Subcharacteristics, 40. Replaceability testing, 45. Requirements-based testing, 23. Risk assessment, 20. Risk identification, 19. 20. Risk impact, 21. Risk level, 20. Risk likelihood, 21. Risk mitigation, 19. 21. Risk-based test strategy, 17. Risk-based testing, 19. SDLC, 11. Agile, 12. 16. Incremental, 11. Iterative, 11. Sequential, 11. 36. Software development lifecycle, 11. Standards, DO178C, 17. ED12C, 17. ISO 25010, 16. 57. OMG DMN, 27. OMG UML, 32. State transition testing, 23. 28. Suitability, 39. Suitability testing, 41. SUMI, 39. 44. Test, 10. Test analysis, 10. 12. Test basis, 15. Test case, 15. Test charter, 18. 23. 36. Test condition, 10. 13. 15. Test data, 10. Test data preparation tool, 52. Test design, 10. 13. 13. Test design tool, 52. Test environment, 17. Test execution, 10. 18. Test execution schedule, 10. Test execution tool, 52. Test implementation, 10. 16. Test Oracle, 15. Test TED, 10. Test development, 10. Test identification, 10.
Certified Tester Advanced Level, Test Analyst, CTAL. Test Strategy, 13. Test Suite, 10. 17. Test Technique, 23. Testing Software Quality Characteristics, 39. Unscripted Testing, 18. Untestable, 47. Usability, 39. Usability Testing, 42. Use Case Testing, 23. 32. User Error Protection, 39. User Error Protection, 39. User Experience, 39. Evaluation, 43. User Interface Aesthetics, 39. User Stories, 48. User Story Testing, 23. WAMI, 39. 44.